Hello there, and welcome to Science for Sleep, where curiosity settles in beside you and questions drift gently enough to help your mind soften at the edges. Tonight we're turning our attention to something you've lived with every moment of your life, but may never have examined closely, something that nudges you forward whether you're ready to move or not. The theme at the centre of this quiet exploration is a simple one to describe, yet endlessly confusing to truly understand. Why does time only move forward? Why is it that each second seems to roll into the next with no option to pause, rewind, or ask for a redo? You wake up each morning a little older than you were before. You walk through your day in one direction. And long after the sun goes down, the same stream keeps carrying you along without permitting even the faintest glance over your shoulder at what already slipped by. Before we wander deeper into that question, I'd love to know something from you. Where are you listening from tonight? And what time is it in your corner of the world? It's always fascinating to think of people spread out across different hours, some settling into the quiet of evening, others starting their day, and a few drifting somewhere in between. We talk about time as if it's a single thing, but you and I are meeting inside completely different moments, even though we're sharing this one together. If you find our slow, curious journey a comforting part of your evening or your early morning, I'd be grateful if you'd consider liking the video or maybe subscribing. It helps this relaxing little space reach others who might need a soft place to rest their thoughts. Still, don't worry about that right now. You're already here, settling into this calm environment, and the only thing I'd like you to pay attention to is the gentle way the mind begins to unwind when it has permission to focus on just one idea at a time. There's no hurry in this exploration. We'll walk through it steadily, the way time itself carries you from moment to moment without racing or asking for your input. Something interesting happens when we start thinking about why time seems to flow only in one direction. We notice how often the experience of life reflects this same structure without us ever naming it. You can remember what happened yesterday, but you can't reach into tomorrow and pull out details the same way. You can watch a cup of tea grow cooler as the minutes pass, but you never see it spontaneously grow hotter while sitting untouched. A stack of books on your desk doesn't accidentally arrange itself into neat order overnight. You don't find shattered glass suddenly pulling together into a whole again. Everything around you seems to follow one orientation, as if the world were gently nudging everything from a state of relative order into a state of greater disorder, step by step. And as you listen, you might notice that thinking about time in a slow, relaxed way feels different from how you usually encounter it. Normally, time pushes you, taps you on the shoulder, reminds you of appointments, responsibilities, and unfinished tasks. Right now, though, it's giving you room to settle in, sink a little deeper into comfort, and let the idea unfold patiently. When we slow down like this, the question begins to shift. It's not just, why does time move forward? But what does moving forward even mean? You might picture time as a path laid out in front of you, but that's just one way of sensing it. Our daily lives encourage that feeling because everything seems to line up into sequences. One event leading into another, conversations forming in linear patterns, meals following hunger, night following day. But the central puzzle remains. Why this direction and not the other? Why is it that you can recall something that happened earlier, but you can't retrieve what comes next? Why are your memories arranged behind you while your expectations are placed ahead? Even the construction of your emotions follows this pattern. Nostalgia points backward, hope points forward, and you rest somewhere in the ongoing middle of both. You breathe out after breathing in. You wake after dreaming. You grow older with every sunrise, not younger or reversed or stuck in place. It's such a deeply familiar experience that it seems almost strange to question it. Yet here we are, easing gently into that question together. As we continue down this quiet path, you might notice that the mind begins loosening its grip a bit. The more you lean into curiosity, the more your attention shifts from the usual momentum of your day toward this softer, slower investigation. And in this setting, the flow of time feels less like a pressure and more like a companion walking beside you. Every moment passes at the same unhurried pace, giving you enough space to observe without rushing. The idea of time moving forward becomes less like a rule and more like a quiet feature of the world that has always been in the background, guiding the rhythm of your life. There's something almost comforting about realizing how structured your experience is, even when everything around you appears unpredictable. No matter how chaotic your workload feels, no matter how many tasks crowd your schedule, the movement of time itself doesn't waver. It continues, consistent and familiar. Even when you're overwhelmed, time never sprints ahead of you. Even when you're impatient, it never slows down to test your endurance. It just keeps unfolding moment after moment in the same direction, creating the conditions that allow memories to form, experiences to accumulate, and growth to happen. But we should take a moment to acknowledge something. The question we're exploring is not simply a matter of clocks or calendars. If it were, the answer would be easy. Of course time moves forward because clocks move forward. But clocks are tools, not authorities. They don't dictate time. They measure it according to the movement they were built to track. The real question sits behind all of that. What is it about the physical universe, the nature of reality itself, that causes everything to unfold the way it does? What is it about the structure of existence that places events in a sequence rather than a mess of directionless interactions? You might think of the world around you right now. The air in your room, the softness of your pillow, the warmth of your blanket. All of these things are arranged in their current state because of what happened earlier. Every object around you follows a chain of causes stretching back in time, a chain you never noticed forming. When you switch on a lamp, the light doesn't appear before the switch is pressed. That sounds obvious, but obvious things often hide deeper truths. The light follows the action because the world doesn't permit those events to reorder themselves. You can't stir milk into coffee and expect it to separate on its own. You can't drop a stone into water and watch the ripples collapse backward into perfect stillness. Everything around you follows this forward sequence so consistently that it forms the backbone of how we understand change itself. And yet, the direction of time isn't something you can point to or hold. It's not something you can set on a table and examine. Instead, it emerges through how events behave and how processes unfold. You learn its direction by watching how things evolve. When a candle burns, the wax melts, the wick shortens, the flame flickers. You witness the transformation and immediately understand which end of the sequence came first. You never see the opposite sequence naturally. The candle doesn't reform itself. The wax doesn't leap upward, neatly arranging itself as if preparing to be lit. This asymmetric behavior is a hint, a clue that something within the structure of the universe consistently organizes events from what appears ordered to what appears less ordered. As you settle deeper into this thought, you might notice something familiar. Even without thinking about physics or philosophy, you live according to this direction every day. You plan for what hasn't happened yet and reflect on what already has. You create memories by moving through time in one direction, and those memories become the framework that lets you make sense of yourself. Imagine for a moment what it would feel like if that orientation were different. If you opened your eyes and your mind registered future events as clearly as past ones. The sense of who you are, how you function, and how your life unfolds would be completely different. The structure of your identity would shift in ways too unfamiliar to articulate. The simple act of waking up would feel like stepping into a story without a beginning or end, and that quiet realization reinforces something subtle. The direction of time isn't just a scientific curiosity, it's a fundamental part of how you understand your existence. As you breathe and listen, the steady pace of this reflection mirrors how time feels in moments when the world gets quieter, when nothing is rushing you, when your thoughts have space to stretch. The whole idea begins to settle into the background of your awareness and become something less intimidating. You don't need answers yet. You don't need theories or equations. Right now, the only thing you need is a calm starting point from which the next ideas can naturally unfold. The movement forward we feel in time will continue to guide us as we explore what gives it that motion. And as we follow this stream of thoughts together, the experience will keep flowing without abrupt stops, so the path ahead feels smooth and steady. The experience of noticing how everything around you seems to follow a single direction in time is something you've lived with for so long that it rarely stands out. You wake up, stretch, get out of bed, and move through your routine with an unspoken expectation that each action follows the next in a reliable sequence. It never occurs to you that the cereal won't pour downward, or that the kettle might boil before it's switched on. These expectations are so embedded into daily life that the idea of them behaving differently feels more like a scene from a confusing dream than something grounded in real experience. The consistency of forward motion is one of those unnoticed features of existence that shapes everything you do, even though you rarely think about it. You may not always be aware of it, but a pattern reveals itself every moment you interact with the world. When you speak, the words leave your mouth and move into the air. When you tie your shoes, your fingers move step by step through motions learned long ago. If you were to watch yourself on a camera, you wouldn't expect the video to rewind unless someone deliberately reversed it. Life doesn't spontaneously play backward. The strange part is that we tend to take this directional flow for granted, even though nothing in our everyday surroundings explicitly announces why things unfold this way. They simply do. As you listen, the idea might settle more clearly that this forward motion is one of the few universal experiences shared by everyone, regardless of age or background. A child building a tower of blocks sees gravity pull each piece downward. An older person watching raindrops slide across a window recognizes the same behavior. No matter who you are, every moment happens after the one before it, and this sequence continues throughout your life. Yet, if you were to ask why time feels like it's always nudging the world along, you'd find that the answer isn't obvious from looking around your room or thinking back through your memories. The familiarity of the experience makes it feel natural, even though it raises questions that aren't easy to unravel. Something helpful at this stage is simply noticing how dependable this one-way movement is. Consider something as simple as lighting a candle. You touch the flame to the wick, watch it catch, and see the wax soften and melt as time passes. You don't expect the wick to rebuild itself, or the melted wax to return to its original position. The transformation only makes sense moving forward. Even if you recorded the process and reversed the footage, your mind would instantly recognize that the reversed version doesn't match anything that actually occurs. Your intuition already knows the direction things should go. It's built from a lifetime of watching events unfold in the same orientation. This consistency is something you internalized long before you ever questioned it. When you were small, you learned which actions led to which outcomes. You learned that dropping a toy made it fall downward, and that spilled juice spread across the table instead of gathering itself back inside the glass. These patterns taught you what to expect from the world, long before you ever wondered why those expectations work. As you grew older, the reliability of these patterns only strengthened your sense that time moves in a dependable direction. That direction forms the framework for how you think, how you make decisions, and how you navigate every day. It's interesting to pause and think about how often you rely on this sequence without consciously noticing it. When you plan a meal, you assume the ingredients won't cook themselves before heat is applied. When you save money, you expect the future to arrive in the same order as always. Even something as simple as watching ice cubes melt in a cup reminds you that the world steadily shifts from one condition into another in ways that can be predicted but never reversed without outside effort. And even that effort doesn't truly reverse time. It creates a new sequence of events that still moves forward, just with different steps along the way. As you relax into this reflection, it might become clearer that the certainty of time's direction doesn't come from anything you can touch or point to. It emerges through how processes behave, how objects interact, and how energy spreads. You learn time's direction by watching how the world naturally moves towards states that feel broader, more spread out, and less organized. A pristine room becomes cluttered unless someone cleans it. A hot cup of tea cools unless reheated. A perfect sandcastle erodes grain by grain in the wind. When you look at these examples, you can sense the same pattern each time. Things move toward arrangements that are easier for the world to fall into than the neat, ordered states they came from. You might think of this as a practical guide the universe follows, even though it never states the rule outright. Order turns into disorder with remarkable consistency, but disorder rarely returns to order on its own. You can stir cream into coffee and watch it swirl into new patterns before blending completely, but you never see it separate on its own. The motion of time is hidden inside that irreversible shift. It's not that time itself reaches in and rearranges anything. It's that the natural tendencies of the world encourage certain changes and discourage the opposite ones. Once you begin to see that, the forward movement of time becomes easier to grasp, not as a mystical flow, but as a direction defined by the way things behave. Even your memories reflect this direction. You remember earlier events because they came before, not after. You don't recall future experiences because they haven't yet caused anything in your life. You can picture your past clearly because the world around you has already changed in ways that created the conditions for your memories to exist. The choices you've made, the people you've met, the places you've visited, each one happened in a direction that never loops back. If you try to imagine the opposite sequence, it doesn't align with anything you've ever experienced. Your thoughts are arranged around this one-way structure, and the flow of your internal life mirrors the flow of the external world. As you continue listening, something else becomes noticeable. Thinking about the certainty of forward motion brings a sense of stability. It offers a framework that explains why life feels coherent. If events were to shift out of order, if effects sometimes preceded their causes, the world would feel disjointed. Predicting anything would become nearly impossible. Your routines wouldn't make sense. And while such a world might sound interesting in fiction, it would be nearly impossible to function within it. The consistent direction of time is one of the things that allows everyday life to work as smoothly as it does, even when things feel overwhelmingly busy or unpredictable. There's also something grounding in the realization that this certainty applies universally. No matter where you are, no matter what you're doing, everything around you participates in this same forward flow. The air cools after heat disperses. Food spoils rather than becoming fresher. A tree grows outward from its seed and never in reverse. Even your heartbeat depends on this sequence. Each contraction comes after the previous one, and your body relies on that reliable order to keep you alive. Time's direction is so deeply woven into the structure of the world that imagining its absence becomes nearly impossible. You might feel that the idea is slowly taking shape within you. The certainty of forward motion is not just a feature of clocks or schedules. It's something embedded in the deepest layers of reality. When you observe anything change, you witness time's direction. When you sense something growing older, wearing down, cooling off, or spreading out, you recognize that direction again. Even in moments when you feel stuck or motionless, the world is shifting around you in ways that never reverse. This is how you know which way time points, not because anyone told you, but because everything around you silently demonstrates it. It often helps when trying to understand why time insists on moving forward, to look not at clocks or calendars, but at the small, ordinary transformations happening around you all the time. You might not notice them unless you pause, but they're always there, quietly shaping your surroundings. Ice melts, heat fades, colours bleach in the sun, leaves dry and crumble. These simple observations share a common thread. Each one shows a shift from something tidy or concentrated into something more spread out, more mixed, or more disordered. And that steady shift hints at something deeper that sits at the core of time's direction. That something is entropy. You've probably heard the word before, maybe in school, maybe in passing, maybe in a context that felt confusing or too distant from everyday life. But entropy isn't an abstract idea, it's a direct part of the world you live in, and it might be the closest thing we have to an explanation for why time seems to have a preferred direction. You can think of entropy as a simple measure of how many different ways something can be arranged without changing what it is in any noticeable way. That sounds technical, but it's actually quite practical when you look at ordinary situations. Imagine a tidy desk with everything neatly placed. In that state, there aren't very many arrangements that still look tidy. But once the desk becomes cluttered, there are countless ways for it to stay cluttered. One page over here or one pen over there doesn't make much difference. The messy state has more possible arrangements than the neat one, and that means the messy state is far easier to reach. You don't need to do anything special for clutter to happen. It happens naturally because there are more ways for things to be cluttered than for them to be organized. Entropy is a measure of that difference, and the world tends to move towards states that are easier to reach. This natural drift toward disorder isn't caused by time itself pushing things around. It's the other way around. The directional behavior of the world's processes is what creates the feeling of time moving forward. That direction comes from the fact that there are far more disordered states available to systems than ordered ones, and once something begins shifting into those states, it rarely, if ever, reverses without an external push. That's why a cup of warm tea cools down on its own. The heat spreads into the air, the energy becomes more widely distributed. It's also why smoke from a candle spreads into a room, but doesn't gather back into the wick. The spread out state simply has more available arrangements. Since the universe tends to move into the states that are easier to occupy, the forward movement of time becomes noticeable through these changes. You might picture this idea in terms of something familiar. Think about an ice cube placed on a table. At the beginning, the water molecules are in a highly organized structure. They're arranged neatly in a solid, locked into position. But the moment the ice begins to warm, the structure loosens. The molecules spread apart and move more freely. There are countless ways for liquid water to arrange itself compared to the very limited number of ways a solid ice cube can stay perfectly structured. Because of that, the ice cube melts. This isn't a mysterious process. It's simply the universe moving from a lower entropy state to a higher one. And in doing so, it gives you a clear example of the direction in which events unfold. The same pattern appears at larger scales too. A match burns, producing gases that spread outward. A building ages as its materials gradually decay. A fresh piece of fruit becomes overripe and eventually spoils. These aren't random accidents. They're the natural paths that systems take when they're allowed to evolve without interference. Lower entropy states, the ones we often call ordered or structured, require very precise conditions. Higher entropy states, the ones that seem scattered, mixed, or worn down, can happen in countless different ways. The world simply transitions into them because they're the most statistically likely. And that consistent shift gives time its asymmetry. It might also help to consider something less physical and more conceptual. Think about the memories you carry. They only move in one direction. You can remember something that happened earlier, but you can't remember something that hasn't happened yet. This isn't just because your brain chooses not to. It's because memories form through physical changes in your neural pathways, and those changes also follow the rules of entropy. They involve chemical reactions, energy transfer, molecular arrangements. All of these behave according to the same principles that guide melting ice, mixing liquids, or decaying structures. Your sense of the past and your inability to access the future are built on the same foundation as every other irreversible process in the world. In this way, entropy becomes not just a guide for how physical systems evolve, but also a guide for how you experience life. Once you begin seeing entropy not as an intimidating scientific term, but as a simple description of how things spread out, mix and shift into more probable arrangements, it starts to feel more familiar. You realize it's something you've witnessed thousands of times without naming it. A freshly opened bag of popcorn slowly stales because moisture and air keep finding new arrangements within it. A bright shirt fades because sunlight breaks chemical bonds in ways that can't be undone naturally. A snowdrift collapses as temperature changes push its structure into a state with more possible configurations. These everyday examples reveal something subtle but important. Time's direction isn't imposed from outside. It emerges from the way matter and energy behave. If you try imagining a world where entropy didn't increase, things quickly feel unusual. A cup of coffee might remain the same temperature forever. A building might never crack or shift. Leaves might stay green without decaying. Food wouldn't spoil, but such a world wouldn't simply feel odd on a practical level. It would lack the foundation for processes that allow change, growth, evolution, or even memory. Without entropy increasing, systems wouldn't have a natural tendency to move from one state into another. Events would lose their sequence. Cause and effect would lose their reliability. The steady one-way structure that forms your understanding of reality would break down. It becomes clearer that entropy's increase isn't a flaw or inconvenience. It's one of the key reasons the universe unfolds in a coherent way. You might find it interesting to reflect on how entropy ties your everyday experience to something incredibly large. The same principle that causes a slice of bread to go stale is linked to how stars burn their fuel, how galaxies evolve, and how the universe itself changes over time. On small scales and large scales alike, systems move from states with few arrangements into states with many. This consistency means that everything participates in the same gradual expansion of possibilities. That expansion doesn't tell you what will happen next, but it confines what can happen. The universe won't spontaneously compress into a more ordered state on its own, because the number of ways to be highly ordered is so tiny compared to the vast number of ways to be disordered. Once you see this pattern, time's direction becomes less mysterious. The world transitions into states that are simply more likely, and those transitions give rise to the sense of forward motion. Even something as ordinary as cooking can help illustrate how entropy shapes your experience. When you heat oil in a pan, the molecules move faster, spread more widely, and take on many new possible arrangements. Adding ingredients mixes things even further. The result is irreversible without deliberate effort. You can't naturally separate every grain of salt, every drop of oil, or every molecule of aroma once they've combined. The final mixture represents a state with more possible configurations. That increase in possible configurations is exactly what entropy describes. It's also what ensures that cooking follows a forward sequence. You chop, you heat, you mix, you taste. None of those steps reverse themselves spontaneously. And because the order of those steps never changes, they reinforce your sense of moving from earlier to later. Some people initially think of entropy as synonymous with chaos, but that can be misleading. It's more accurate to view it as a measure of how broadly something can be arranged. A room with books scattered everywhere has higher entropy than a carefully organised library, not because it's chaotic in an emotional sense, but because there are many more ways for objects to be scattered than arranged precisely. Once you understand this, the connection between entropy and time grows clearer. When you clean a room, you're imposing order. You're reducing entropy. But the moment you stop maintaining that order, entropy begins increasing again, not because of time forcing anything, but because disorder is easier to fall into. The world simply relaxes into states with more possibilities. Thinking about entropy as time's quiet compass helps you appreciate the underlying simplicity of the concept. You don't need equations to observe it. You only need to look at the natural unfolding of events. Things cool down, they break, they mix, they decay, they spread, they crumble. These tendencies don't contradict one another. They all point in the same direction. That shared direction is the reason you feel time passing. When systems move from less probable states into more probable ones, they create a sequence that you can recognize. The arrow of time arises from those sequences, shaping the landscape through which your experiences flow. The idea begins to feel less like a distant scientific principle, and more like a gentle guide woven into the world you interact with constantly. Each moment in your life is supported by this quiet compass that ensures events unfold in a stable direction. The warmth leaving your tea, the wrinkles forming on your favourite sweater, the slow fading of a photograph. These small details reflect the same universal tendency. None of them reverse themselves naturally, and this subtle irreversibility creates the flow you recognize as the passage of time. There is something reassuring about noticing how time's direction shows up in the things around you, but that observation naturally raises a larger question. If so many processes in the world move from one state into another because those later states are easier to reach, then something must have set the starting conditions that made this direction possible. If the world continually moves from states of lower entropy into states of higher entropy, then the very first moment of the universe must have been arranged in a remarkably low entropy state. Otherwise, there wouldn't be any gradual rise, no sense of progression, no directional unfolding. The question then becomes, why did the universe begin that way? And what does that beginning tell you about why time moves forward? It helps to imagine the universe not as a sprawling space filled with stars and planets, but as something that once existed in an incredibly compact, nearly featureless state. Not because we're drifting into imagination, but because every measurement, every theoretical framework, and every observation of cosmic history points to the fact that the early universe was astonishingly uniform. Temperature was nearly the same everywhere. Matter was spread out evenly. There were no galaxies, no clusters of stars, no swirling dust clouds. In this unusually smooth condition, the universe held a surprisingly low amount of gravitational entropy. You don't need to translate that term into anything complicated. It simply means that although the early universe was hot and energetic, it was arranged in a way that did not yet take advantage of the countless possible configurations that gravity would later allow. Thinking about it in a simple way, a smooth distribution of matter leaves very few options for rearrangement. It's like having a table covered in identical grains of sand spaced evenly apart. There aren't many different ways to rearrange it while keeping everything evenly distributed. But once the arrangement starts clumping, piling, settling, or gathering, the number of possibilities increases dramatically. The early universe was in that evenly spaced, uniform state. It had the potential to explore a vast number of more complex arrangements, but it hadn't done so yet. That smoothness is what made entropy low, and because the universe expanded from that starting point, everything that followed emerged along a pathway where entropy could steadily rise. That rise is one of the reasons time took on a direction. As you relax into that idea, it might feel less mysterious than it seemed at first. The early universe set the stage for everything that would follow simply by being arranged in a state far from its maximum complexity. Every structure that formed afterward, stars, galaxies, planets, oceans, mountains, weather patterns, biological life arose because the early conditions allowed matter and energy to evolve into states with more possible arrangements. When you look at the night sky, you're seeing the outcome of that process stretched across enormous distances. Every galaxy spinning in the distance, every cluster of stars, every cloud of dust carries the imprint of that early low-entropy origin. The interesting part is that nothing about this origin felt directional in the way you now experience time. There wasn't a ticking clock. There wasn't a moment when the universe stopped to decide which way time should move. Instead, the direction of time appears as a natural result of how the universe began. Because the beginning was unusually ordered compared to what would eventually become possible, the universe had a path to travel that always led towards states with more available configurations. The earliest conditions effectively created the slope along which entropy would increase, and that slope became the arrow of time you experience through every irreversible process in the world. If you look at the universe today, it might seem chaotic compared to its early state. There are stars exploding, galaxies colliding, planets shifting, black holes forming, and energy scattering across enormous distances. These dramatic events give a sense of a universe full of motion and complexity. But beneath that surface activity lies a simple fact. Every one of these changes is part of the same long trajectory that began the moment the universe started expanding. The early uniformity allowed gravity to gradually pull matter into dense regions, forming structures. Those structures heated, ignited, collapsed, and produced even more complexity. Each step increased the number of possible arrangements for the universe, and this steady increase is what gives you the sense that the universe has been unfolding through time rather than looping, reversing, or standing still. There's something grounding about seeing this connection between the larger scales of the universe and the smallest details of your daily life. The reasons your tea cools, your meals cook, your clothes wear out, or your memories form are all tied to that first moment of cosmic organization. Without that unusual initial state, the universe might have begun in a condition where entropy was already maximized. In such a case, nothing would change. No stars would form, no processes would unfold, no directional behavior would appear. Time, in any meaningful sense, wouldn't have a direction, because there would be no gradient to follow. The existence of a forward-moving timeline depends entirely on the universe not starting in its most probable state. It began instead in a rare, highly ordered one, giving everything that followed room to evolve. You might think of this in a more immediate way. When you walk into a room that's perfectly tidy, it has only a few possible ways of remaining that way without effort. A slight movement, a dropped item, a shift in airflow can begin altering the arrangement. Once the space becomes cluttered, there are countless ways it can stay cluttered. The tidy room represents low entropy, and the messy one represents high entropy. The early universe was that tidy room on an unimaginable scale, and because it began in such a restricted state, it had more pathways to move into than to remain as it was. The expansion that followed allowed entropy to increase, not in a forced way, but simply because there were so many more possible states for the universe to explore. As you listen, it might become clearer that time doesn't push anything forward. Instead, the forward motion emerges because the universe's earliest configuration created a landscape where moving into states of higher entropy is overwhelmingly likely. That likelihood builds the forward direction you feel. The universe didn't need a clock to establish that direction. It only needed to begin in a state where the future held far more possible outcomes than the past. Every irreversible event in your life traces its foundation back to that simple fact. It's interesting to consider how expansion itself plays a role. As the universe expands, space stretches, matter spreads, and the regions where gravity can form structures become more pronounced. That stretching increases the number of ways matter can distribute itself. Expansion doesn't force entropy to rise, but it creates opportunities for more configurations to become possible. Without expansion, the universe would have fewer ways to evolve, and the direction we associate with time might look very different. Expansion lets small density variations grow into galaxies, stars, planets, and everything else. The formation of those structures creates new processes, new heat transfers, new chemical interactions, and new pathways for entropy to rise. In that sense, the expansion of the universe acts as a quiet mechanism that encourages complexity, variety, and change. As we reflect on these ideas together, you might notice that the universe's beginning wasn't just a moment in time. It was the foundation that shaped your experience of time itself. The direction you live through is inseparable from that starting point. Every memory you have, every thought you experience, every change happening around you is connected to the fact that the universe began in a state far from equilibrium. The structure of time as you understand it isn't imposed by any cosmic authority. It's a natural result of the conditions that existed when everything first emerged. Letting that thought rest for a moment gives space for another idea to settle. If the early universe created the circumstances that allow entropy to rise, then the events that happen today, from the melting of ice to the aging of stars, are simply the ongoing continuation of a process that began long ago. You never experience the beginning directly, but you feel its influence through every irreversible moment. Understanding that connection helps explain why time seems to move forward in such a steady, consistent way. It's not that the universe is enforcing a rule. It's that the universe is following the consequences of its own starting point. Nothing about this explanation makes time feel less real or less personal. If anything, it deepens the sense that your experience is part of something larger. The direction you move through is shared with galaxies billions of light years away. The memories you form align with the evolution of stars. The cooling of your evening drink reflects the same principles that govern enormous cosmic structures. You're living within a universe that has been unfolding from its first moment, and the flow you feel is part of that expansive, ongoing transformation. Once you know that the direction of time is tied to the universe's beginning, another question naturally emerges. What kinds of events in everyday life reveal this direction most clearly? And why do some processes feel irreversible, while others can be undone with effort? There is something instantly recognizable about certain events in daily life. You drop an egg on the kitchen floor and it breaks every time. The shell cracks, the yolk spreads outward, the edges thin as they slide across the surface. If you've ever watched it happen, you know immediately that the process has a direction. It never goes the other way. You never see the spilled yolk pull itself inward, or the cracked shell gather up the fragments and rebuild itself. It doesn't matter how often you picture the reverse. The real world never behaves like that. And this simple observation points to something central about how the universe works. The direction of time is written into the difference between what can happen easily and what cannot happen without enormous effort. It isn't the egg's fault that it doesn't reassemble. It's that the world doesn't provide a natural pathway for that reversal. When you drop an egg, you're watching something transition from a state with a very limited number of possible arrangements into one with countless possibilities. A whole egg sitting in your hand is a highly specific arrangement. The shell is intact, the contents are contained, and the entire structure occupies a narrow range of possibilities. Once the egg hits the ground, the number of possible arrangements explodes. The shell can crack in hundreds of ways. The yolk can spread unevenly. The white can take on irregular shapes. Every tiny variation in angle, speed, texture, and temperature influences how the final mess looks. There are so many ways for a broken egg to exist, and so few ways for an unbroken egg to exist, that the world simply moves toward the more probable state. This behavior isn't a special property of eggs. It applies to countless situations. A broken glass doesn't leap back together. A spilled drink doesn't collect itself. A burnt match doesn't regain its fuel. These events happen in only one direction because the alternative paths are so improbable that the world never stumbles onto them naturally. You would need an astronomical level of coordination to reverse these processes. Every particle involved would have to move exactly right at exactly the right moment. The odds are so low that even if the universe continued for unimaginable lengths of time, you still wouldn't expect to see it happen once. As you think about this in a quiet, relaxed way, it becomes easier to see that the direction of these processes isn't enforced by a rule printed somewhere in nature. It's a consequence of probabilities. The intact egg represents a very limited number of arrangements. The broken egg represents a nearly endless number. Moving toward the many is easier than moving toward the few, and because the world follows the path of least resistance, it settles into states with more available configurations. That simple shift is enough to make time feel like it moves forward. There is something steadying about noticing how this principle shows up in places you might not expect. Consider a scoop of ice cream left out on the counter. At first, it holds its shape. It has structure and definition. But as it warms, it relaxes and sinks. The melted puddle can take countless shapes, depending on how the surface tilts or how long it has been sitting there. The original shape had few permissible configurations. The melted one has many. That's why the melting feels natural and the reverse feels impossible. You never walk into the kitchen to find the puddle has spontaneously formed back into a neat scoop. There are simply too many ways for the melted state to exist compared to the original. Even something as calm as dust settling on a surface shows the same tendency. Dust particles have numerous ways they can spread across a table, a shelf, or the edge of a windowsill, but they have almost no way to gather themselves into a tidy pile without help. You never watch dust jump together into a neat cluster. The settled state is one of high entropy, with many possible arrangements. The tidy pile is low entropy, with only a few. The world naturally drifts toward the state with more options, not because it aims to, but because probability strongly favours it. When you observe this pattern, you can feel the presence of time's direction inside it. You don't need to look at clocks. You don't need equations. You simply observe how things move from states that require careful arrangement into states that don't. If you closed your eyes and someone described a process to you, you could usually tell which way it ran. A cup cooling, a candle burning, a leaf decomposing, a crumbed cookie crumbling further. These events flow in a particular orientation, and the reason broken eggs don't unbreak is the same reason these other processes don't reverse. You might think that if you had perfect technology or perfect tools, you could gather the pieces and attempt to restore the egg. But even if you did that, you wouldn't be reversing the process. You would be creating a new sequence of events that restores an appearance of order, not turning back time. The broken egg would not reassemble itself. You would be introducing energy, performing work, resetting conditions. Entropy would decrease locally because you were actively pushing it downward. But beyond the boundaries of your action, entropy would still rise elsewhere. The universe, as a whole, doesn't allow entropy to spontaneously decrease. It only permits local decreases when they're offset by increases in the wider environment. It's reassuring to realize that this same relationship between order and disorder underlies many familiar experiences. Think of baking bread. You mix ingredients in a bowl, combine them into dough, let the dough rise, knead it, shape it, bake it. Each step changes the arrangement of particles, spreading, mixing, heating, and reacting. Once the bread is baked, you cannot unbake it. There is no natural sequence that leads back to raw ingredients. That doesn't mean the baked loaf is more complicated. It simply means that the baking process created countless new chemical configurations that can't be undone without starting entirely new processes. Those processes still move in a forward direction. Or consider the way a book falls apart over time. The paper yellows as molecules in the fibres break down when exposed to oxygen and light. The glue along the spine stiffens or cracks. The edges fray. Every one of these changes spreads the book into states with more possible variations. To reverse them, you would need to reform broken molecular bonds, reconstruct the arrangement of fibres, and undo the interactions that caused the original breakdown. The amount of coordination required far exceeds anything the world produces naturally. That's why worn-out books don't spontaneously become crisp and new again. What's interesting is that even microscopic systems reflect the same forward movement. When heat enters a cold object, the energy spreads until it reaches an even distribution. Once the distribution becomes uniform, there's no preferred path for reversal. The uniform temperature state has many possible micro-level arrangements. The earlier state, where heat was concentrated, represents a narrower range of configurations. The spread-out condition is easier to reach and harder to leave. The forward direction emerges automatically. Even your own thoughts experience this principle. A moment of surprise, excitement, or confusion triggers chemical pathways in your brain that follow irreversible directions. Once those pathways activate, memories form, signals move, patterns shift. These sequences only run one way because they depend on underlying processes that follow entropy's lead. The same rule that explains a broken egg also explains why you cannot unlearn something by wishing it undone. You can replace the memory with a new one, revise your understanding or shift your perspective, but you cannot reverse the physical events that created it. Reflecting on these examples helps you see that the direction of time isn't an add-on to the universe. It arises directly from the way systems evolve. When you see a broken egg, you're not just witnessing a mess on the floor, you're seeing evidence of the universe favouring states with more possible arrangements. You're seeing the natural progression from a precisely arranged condition into a broader, more flexible one. And every irreversible event operates on the same principle. There's something calming about breaking the question down to this level, because it shows that the world behaves consistently. You don't need to worry about your morning routine starting to run backward, or the contents of your refrigerator spontaneously reassembling into earlier forms. You can rely on the fact that things around you only flow in one direction. That predictability allows you to plan, remember, and function within the world. Without it, life would feel incoherent. If processes could spontaneously reverse, you'd have difficulty trusting anything that happened. The stability you feel in your experience is supported by the irreversible nature of entropy-driven events. When you consider this slowly, you begin to appreciate how the simple behavior of a broken egg reflects something universal. It isn't just a kitchen accident. It is a small, accessible example of the same principle that governs the evolution of stars, the formation of galaxies, the cooling of planets, and even the changing patterns in your own life. The universe is filled with processes that move from the narrow to the broad, from the constrained to the possible, from the organized to the dispersed. Each one reinforces the direction you experience as the passage of time. It's often easy to think of time's direction as something happening out in the world around you. Eggs break, candles burn, ice melts, and all of these familiar processes move in only one direction. But there is another place where the arrow of time shows up even more clearly, and that place is your own mind. You don't need a physics lab to feel it. You sense it every time you recall a memory, form a thought, recognize someone's voice, or sit quietly waiting for your mind to settle. The way you experience time is tied deeply to how your brain stores information, how it creates meaning, and how it forms a sense of who you are. Time moves forward in the world outside you, but it also moves forward inside you. Understanding one helps you understand the other. If you pause for a moment and think back to something that happened earlier today, maybe a conversation you had or a task you completed, the memory probably feels anchored behind you. You don't need to analyze it to know it happened before this moment. The sensation arrives naturally. You also can't pull up a memory of something that hasn't happened yet, even if you try. That asymmetry is powerful. It shapes the way you make decisions, how you relate to other people, how you interpret events, and how you construct meaning from experience. You know the past, you imagine the future. But the future never shows up with the clarity or detail that the past provides. This difference isn't simply a matter of perspective. It comes from physical processes happening inside your brain. When you encounter something new, an image, a sound, a person, a scent, your neurons adjust their connections. Synapses strengthen, weaken, activate, or reorganize. Proteins change shape. Electrical signals travel. Patterns form. All of this creates a trace of what happened, and those changes move only in one direction. Once a memory has formed, the physical state of your neurons is different than it was before. That change can't spontaneously reverse itself. Once something has happened inside your neural network, your brain doesn't revert to the state it held earlier. This is one of the clearest examples of how the direction of time lives within you. Memories aren't just stories you carry around. They're physical modifications of your brain structure. Each memory is a pattern of activity that exists because earlier processes unfolded in a particular order. You can reinforce a memory, reshape it, forget it, or reinterpret it, but you can't uncreate the physical changes that once occurred. Even forgetting doesn't erase the earlier direction. It adds new changes that overlay or weaken the old ones. Everything continues moving forward. Meaning develops in a similar way. You attach significance to events based on what came before. The first time you meet someone, you build impressions. Later interactions build on those impressions. Over time, your understanding grows more layered, more nuanced. And this layering follows a one-way sequence. You never begin with final understanding and then gradually revert to first impressions. You always accumulate meaning across time. Even if your opinion shifts, the shift itself is a new moment, influenced by everything that preceded it. There's something calming about recognizing how consistent this structure is. It means your life is built from a sequence of events that give rise to memory. Memory shapes meaning, and a meaning shapes your sense of self. You aren't static. You aren't repeating the same moment over and over. You're travelling through a landscape shaped by what you've learned and what you've experienced, and all of that movement is possible because the physical processes in your brain move in a single direction. Some people think of memory as a kind of internal archive, a library stored in the mind. But that analogy doesn't fully capture how dynamic the process really is. When you recall something, the act of remembering triggers new neural activity, which slightly alters the memory each time. Remembering is not the same as replaying a recording. It's more like rewriting the memory while you retrieve it. This too only happens in one direction. You can modify a memory, reinforce it, soften it, or distort it, but you cannot unwind the sequence of changes that originally created it. The arrow of time is built into this continuous reshaping. If time were reversible, your memories would remain fixed when recalled, lacking any growth or adjustment. But because time moves forward, every act of remembrance becomes part of an ongoing process. You're always adding to the network of connections that define your understanding. This gives your memories their living character. They're not static images. They evolve. It's also important to recognize that your mind uses the direction of time to organize your experience. Without that direction, you would struggle to make sense of events. Imagine receiving information in the wrong order, a cause arriving after its effect, a reaction happening before the trigger. Communication would lose clarity. Planning would become impossible. Emotional responses wouldn't match circumstances. Even something as simple as crossing a street would become overwhelming, because you wouldn't know which moment was the most recent one. Your mind relies on the assumption that present experiences follow past ones. This isn't just habit, it's how your brain is wired. The predictions you make about the world, when to move, how to speak, what to expect, depend on the understanding that earlier events preceded this moment. That directional assumption is baked into your brain's entire organizational structure. Even your sense of identity emerges from this one-way arrangement. You know who you are because you remember earlier versions of yourself. You remember the choices you made, the paths you followed, the experiences that shaped you. These memories form a continuity, a thread that connects your past self to your present self. If time didn't move forward, this sense of identity wouldn't hold together. You would experience yourself as a series of isolated moments rather than a continuous being. The story of your life requires time to have a direction. When people reflect on meaningful moments, they often speak about them as turning points, a decision, a realization, a change in perspective. These shifts gain significance because they come after earlier events, not before. Something happened that caused you to think differently. Something else led you to respond in a new way. The meaning comes from the direction. Without that forward flow, meaning wouldn't accumulate. Experiences wouldn't lead anywhere. The emotional depth of your life would lose its structure. Even anticipation reflects this one-way movement. When you look ahead to something you hope for or something you fear, your mind constructs its expectations based on patterns from the past. You imagine outcomes because your brain organizes information based on sequences that have already occurred. The future remains unknown, but the way you think about it is shaped entirely by the irreversible past. Your thoughts about tomorrow depend on your memories of yesterday. This reveals another important aspect of time's direction. Your mind doesn't just record the past, it uses the past to build models of the future. Each of these models is shaped by lessons, observations, and patterns embedded in your memory. You expect the stove to heat food because every earlier experience tells you it does. You expect a friend's laugh to sound familiar because you've heard it before. These expectations only make sense because time flows from earlier to later, not from later to earlier. Your brain uses that flow to navigate the world. People sometimes wonder why emotional experiences can feel heavy or lasting. Part of the answer comes from the physical processes behind how memories form. An intense experience, joyful or painful, creates strong chemical and structural changes in the brain. These changes reinforce themselves over time because each recollection triggers further modifications. The direction of time is reflected in these layers of reinforcement. An event gains meaning not just when it happens, but each time you revisit it. That repeated reinforcement is possible only because time continues to move forward. This doesn't mean that meaning is fixed. It often shifts as you understand more. Something that once felt confusing can later feel clear. Something that once felt overwhelming can become manageable. These shifts follow a pathway. The earlier version of the experience becomes part of the foundation for the new understanding. Time allows these reinterpretations to accumulate. Without the arrow of time, nothing would evolve. There is another dimension to this, one that sits quietly in the background of daily life. Your mind not only remembers events, but it also remembers the order of events. If you eat a meal and then see the dirty dishes, the sequence makes sense. If you saw the dirty dishes before eating, the situation feels predictable. But if the sequences were reversed, your experience would feel disjointed. Your brain is built to recognize the order of events as a crucial part of understanding what they mean. The arrow of time isn't only about remembering, it's about recognizing patterns that unfold in a consistent direction. What's interesting is that even dreams follow this structure. The events in dreams don't always follow logic, but they follow time. Images appear in sequence, thoughts evolve, emotions shift. Even in the loose, drifting environment of sleep, your mind still organizes experience in a forward orientation. It doesn't produce the future and then the past. It produces a stream of moments that feel connected. Even when dreams distort space or identity, they rarely distort the direction of time. Some neurological conditions can disrupt the formation or retrieval of memories, but even in those cases the direction remains intact. Someone might lose the ability to form new memories, but they still move forward through time. They can still respond to new events. They can still react to changes in their environment. The inability to encode memories doesn't reverse time. It simply prevents new layers of meaning from being added. The direction remains. Understanding all of this helps explain why the arrow of time feels so natural. It isn't just an external phenomenon. It's deeply tied to how you think, feel, learn, remember, and grow. The structure of your mind is built around this directional flow. Every thought you experience is shaped by what came before it. Every decision carries the residue of earlier events. Every memory reflects an irreversible sequence that formed it. As this understanding settles into place, it becomes easier to appreciate how the mind's arrow aligns with the physical arrow that governs eggs breaking, candles burning, and ice melting. Both arise from processes that move in only one direction. Both depend on irreversible changes. Both create the sense of progression that defines your experience. It's easy to look at the world and see only disorder. You walk through a day filled with unpredictable moments, shifting plans, unexpected interruptions, and objects that never quite stay where you left them. A drawer you organised yesterday somehow becomes cluttered again. A stack of papers grows uneven. A room fills slowly with the everyday traces of living. Even outside, weather changes without warning, leaves drift in uneven patterns, and water ripples differently each time you disturb its surface. At first glance, it can feel as if everything is sliding into chaos without any underlying structure. But if you slow down and examine what's happening more carefully, you start to notice a consistent pattern that lies beneath the surface. The apparent disorder of the world isn't random. It follows rules so steady that they guide almost everything you experience. This hidden order is directly tied to the way time moves forward. You can begin noticing this hidden order in small, familiar moments. Think about pouring a handful of cereal into a bowl. The pieces scatter, some bounce, some land neatly, others spill over the edge. Nothing about the pattern seems predictable, yet the scattering follows a consistent principle. The cereal spreads out because there are countless ways for it to be scattered, and only a few ways for it to be perfectly arranged. Even though you don't calculate every motion, the outcome isn't surprising. You've seen similar events many times before, and they always move toward a more spread out state. That tendency is the order beneath the apparent chaos. This doesn't mean that the universe prefers disorder in an emotional sense. It simply means that systems naturally drift toward states with more possible arrangements. When you watch leaves swirling on a windy day, they may seem to move unpredictably, but the overall pattern is shaped by air currents, temperature differences, and the natural spread of motion across many particles. The path of any individual leaf may be hard to trace, yet the general trend reflects the same underlying rule. Energy and matter disperse unless something actively prevents them from doing so. Time's direction is visible inside those drifting leaves because they move in a way that cannot simply reverse itself. Consider another example you see almost every day without giving it much thought. When you mix sugar into a cup of tea, the grains dissolve, disappearing into the liquid. They spread until they are evenly distributed. You never see the grains reappear at the bottom of the cup in neat piles. They follow the path of greater dispersion because that path contains far more possible configurations. The apparent chaos you notice when you stir the tea is guided by a predictable underlying tendency. That predictability is the quiet order shaping the event. Even sound reflects this hidden order. When you drop something on the floor or clap your hands, the sound waves spread outward in all directions. The vibrations move through the air, growing weaker as they disperse. You never hear sound gathering back into the object that made it. It always spreads. The outward direction is built into the physics of how waves move. This spreading increases entropy, and once again you see evidence of time's forward motion in the process. If you look at how heat behaves, the same pattern appears. A warm object cools when left alone because heat naturally drifts from regions of high concentration to regions of lower concentration. You can warm the object again if you add energy, but you can't expect the added heat to spontaneously appear on its own. Even though the cooling might feel chaotic, one spot cooling faster, another slower, it follows predictable rules that guide the overall direction. These rules are rooted in how microscopic particles share energy with each other, gradually moving toward a more even distribution. That gradual leveling process happens in one direction only. It becomes clear, as you consider these examples, that the world's apparent messiness arises from countless individual events, each small and unpredictable, yet each following a larger pattern. The pattern is the tendency of systems to move towards states with more possible arrangements. That tendency is the hidden order beneath what looks like chaos. You might not be able to predict the exact position of every grain of sugar in your tea, or every leaf in the wind, but you can predict the overall direction those systems will take, and that direction points forward in time. There is something calming in recognizing that complexity doesn't mean randomness. When you see a room becoming cluttered, you're watching the natural outcome of many small actions accumulating over time. Each dropped item, each unfinished task, each object left where it happened to land contributes to the gradual drift toward disorder. Nothing about this drift is surprising once you understand that the ordered arrangement required precise placement, and the disordered arrangement allows countless possibilities. The world doesn't need to be chaotic for clutter to form. It only needs to follow the simple rule that higher entropy states are more probable. You can even see this hidden order in nature on larger scales. Weather patterns appear unpredictable hour to hour, but they follow stable principles. Air moves from high pressure to low pressure. Temperature differences create circulation. Moisture condenses and evaporates according to well-understood rules. Individual clouds may form in irregular shapes, but the processes behind them follow steady patterns. Over long enough timescales, climates settle into rhythms shaped by these directional tendencies. Rain falls, rivers carve paths, mountains erode, and landscapes transform in ways that always move forward. None of these processes reverse spontaneously. Another place where this hidden order becomes visible is in your body. When your cells use energy, they release heat, byproducts, and molecular waste. These must be carefully managed because biological systems depend on maintaining low entropy in specific regions. Your body works constantly to prevent entropy from rising too quickly in places where structure is essential. But even with that effort, overall entropy always increases. Cells break down material, convert energy, and release heat into the surrounding environment. The processes inside you follow the same irreversible direction seen in your surroundings. The structure of life itself depends on managing entropy temporarily, but not defeating it. The hidden order behind these processes is the same order that makes time meaningful to you. Without it, your experience of each moment would feel disconnected. If systems could spontaneously reverse their direction, the world would feel unstable. A cooled cup of tea might suddenly become hot. A cracked window might suddenly mend. A worn object might regain its original condition without reason. These reversals don't happen because they would require a shift into states with far fewer possible configurations. The stability you feel in everyday life arises from the fact that these reversals are practically impossible. As you reflect on this gently, you may start to see that the hidden order beneath everyday chaos offers a kind of quiet assurance. Even though things appear messy or unpredictable at times, they follow rules that keep events unfolding in a consistent direction. If you spill something, it spreads. If you heat something, it cools afterward. If you organize something, it gradually drifts back toward disorder unless you intervene. Each of these observations might seem trivial on its own, but together they define the character of time as you experience it. There is also a psychological dimension to this. Your mind becomes accustomed to expecting these directional behaviors, so much so that you rarely think about them. You know that objects fall, not rise. You know that scattered items won't gather themselves. You know that heat fades rather than appears out of nowhere. Your expectations are trained by the hidden order of the world. This training is so deep that when something behaves in a way that doesn't match these expectations, like a camera glitch that runs footage backward, it immediately feels unnatural. Your mind recognizes the break in the pattern. This recognition shows how closely your internal sense of time aligns with the physical processes around you. You feel discomfort when the pattern of real-world events is disrupted, because the arrow of time is something you've internalized. It gives structure to your decisions and your understandings. It forms the background of your thoughts. And the certainty of that arrow depends on the hidden order beneath the surface of everyday chaos. Even in moments that feel unstructured, when your schedule changes unexpectedly, or when events pile up in ways you didn't foresee, you're still moving through a world shaped by that underlying order. The unpredictability you experience isn't due to the absence of structure. It arises because many small interactions overlap in complex ways. But the direction those interactions take never varies. They always move towards states with more possible arrangements. The arrow doesn't waver. If you look at long periods of time, you can see how this hidden order shapes entire environments. Buildings age, materials degrade, forests regrow and then burn, rocks erode into sand, rivers shift their paths. Even though these transformations seem chaotic or slow or uneven, they reflect consistent processes influenced by gravity, heat, pressure, and chemical reactions. Each process follows the same directional logic that determines how sugar dissolves in tea or how sound spreads through air. The scale changes. The rule does not. As you take in these ideas, the world around you may start to feel less random. Time's arrow no longer appears as a mysterious force, but as the natural outcome of systems moving through their available possibilities. The apparent chaos you see every day is not an absence of order. It is the surface appearance of countless small events guided by a steady rule. That rule ensures that everything moves in a direction you recognize as forward. If everyday processes reflect a hidden order that aligns with time's arrow, then the next natural question is how these directional tendencies combine with larger cosmic forces to shape the flow of reality. It's natural, after spending so much time noticing how the world moves forward, to wonder whether things could ever have been different. When you see that eggs break but never unbreak, that heat spreads but never gathers by itself, that memories form but never run in reverse, you might begin to imagine a moment before this direction appeared. You might ask whether time always behaved this way, or if its familiar orientation was something that developed only after the universe settled into certain conditions. It's an intriguing thought, partly because you've lived your entire life immersed in a one-way flow. Considering that the universe might once have behaved differently can feel like trying to imagine a world where gravity doesn't point downward. It challenges the basic assumptions your experience is built upon. To begin exploring this question, it helps to return to the earliest moments of the universe, but with a different perspective than before. Earlier we considered how the initial conditions created a path along which entropy could rise, but now the question shifts. Instead of asking why entropy increases, you begin asking whether there was ever a moment when its increase didn't define the arrow of time at all. If entropy gives the universe a direction, did a moment exist when the universe had no direction? Or even more puzzling, could the direction have been different? This leads to an idea that is both simple and strange when you first encounter it. Before the universe had enough structure to support complex processes, there may not have been a meaningful distinction between past and future. If every region of space looked nearly identical, if temperatures were almost perfectly even, if nothing had yet clumped into stars or formed gradients or produced irreversible processes, then the familiar arrow of time might not have existed in the way you now experience it. The universe may not have had backward or forward. It may have simply existed in a condition where those concepts had no significance. That's because direction, as you experience it, relies on change. More specifically, it relies on the tendency of systems to evolve into states with more possible arrangements. But if the earliest conditions didn't yet allow that evolution to begin, the arrow would have been undefined rather than reversed. Imagine a perfectly smooth field with no variation. If you were asked which way the slope points, there would be no answer, not because the slope points upward or downward, but because a slope doesn't yet exist. Direction becomes meaningful only after variations appear. This notion doesn't imply that events ran backward in any literal sense. Instead, it suggests that before the universe developed enough internal contrast for entropy to rise, there may not have been a preferred direction at all. You can think of this as the universe being in a kind of suspended neutrality, not moving backward or forward, simply existing in a highly uniform state. Only when expansion, cooling and density fluctuations began to break, that symmetry did direction form. But what about the question of whether time could have flowed backward in a genuine physical sense? It's a compelling idea, and it often appears in fictional stories or speculative thought experiments. To make sense of it scientifically, you have to understand what reversing time would truly mean. It wouldn't simply involve events happening in reverse order. It would require every microscopic particle, every quantum interaction, every distribution of energy to move into states with fewer possible arrangements rather than more. This would be equivalent to water flowing uphill everywhere, heat concentrating spontaneously, memory erasing itself structurally, broken objects reassembling, and processes unrolling instead of unfolding. Nothing in the known laws of thermodynamics suggests such global behavior is possible under ordinary conditions. However, when you examine the laws of motion that govern the smallest particles, something interesting appears. Most of these laws don't care about direction. If you reverse the motion of every particle in a closed, perfectly controlled system, the laws would allow the reversed motion just as easily as the forward motion. This symmetry often surprises people because it seems to contradict the irreversible world we experience. But the symmetry exists only in theory. In practice, the probability of reversing every motion perfectly is so small that the universe never finds its way into those pathways naturally. This distinction between theoretical reversibility and practical irreversibility is what creates the feeling that time's arrow is absolute. You never see reverse processes not because they violate fundamental rules, but because the number of conditions required to make them occur is unimaginably tiny. The universe doesn't search for those states. It moves toward the overwhelmingly more common ones. But this brings back the original question. Could an earlier universe have faced different probabilities? Could the conditions have been arranged in such a way that time pointed in the opposite direction. This idea has been explored by physicists considering whether regions of space might experience time differently depending on how entropy behaves locally. In certain speculative models, it's imagined that a universe could expand from a low entropy state and then contract back into one, creating a second arrow that points in the opposite direction. In such a model, two regions of the universe might experience time flowing outward from a shared low entropy moment, but in opposite directions from each other. To understand how this might work, imagine a central moment where entropy is at its minimum. On one side of that moment, entropy increases in one direction. On the other side, entropy increases in the opposite direction. To observers on each side, time would feel like it flows forward, even though each region's arrow points away from the central moment. From one perspective, the other region would appear to be moving backward, but no observer within either region would ever notice anything unusual. Each side would have memories of states behind them and expectations for states ahead of them. Each side's internal processes would follow the same irreversible progression. But the two sides would disagree about which direction constitutes the future. This picture is speculative, and there is no direct evidence that our universe behaves this way. But the idea highlights something important. Time's arrow doesn't arise from the laws of motion themselves. It arises from boundary conditions, the starting conditions that set the framework for how entropy evolves. If you change those conditions drastically, you might create a system where time points in a different direction relative to another system. Another possibility that scientists have discussed is whether time might behave differently near certain extreme environments, such as regions near black holes or near theoretical singularities where space and time are distorted. These ideas don't involve time running backward, but instead suggest that the structure of time might be radically different in conditions far removed from ordinary experience. Reversal doesn't occur, but direction becomes more complex than the simple forward progression you're familiar with. But when people ask if time could have flowed backward once, they often mean something more intuitive. They wonder whether there was ever a moment when processes naturally tended to move toward more order instead of more disorder. And the answer appears to be that the earliest universe didn't move toward greater order because it was already in an unusually ordered state. It didn't evolve from high entropy into low entropy. It expanded from a low entropy beginning into conditions that allowed entropy to rise. That means time's arrow wasn't reversed, it simply hadn't emerged yet in the form we experience. If you follow this idea slowly, it becomes clear that the universe didn't need a sudden change in rules to create time's direction. It needed contrast, it needed gradients, it needed differences in density, temperature, and distribution. Once those differences formed, systems began evolving in a way that always increased entropy, and once that happened, the arrow of time appeared as a natural outcome. You can even see a faint reflection of this in everyday conditions. If you walk into a room where everything is perfectly arranged, it's difficult to tell which direction things are likely to move. The room doesn't contain enough contrast to hint at what will change first, but as soon as you interact with the space, picking something up, placing something down, shifting the air or temperature, new gradients form, and the room begins moving toward higher entropy. Only after that shift does direction become obvious. The same idea applies at a cosmic scale. It's interesting to imagine how alien the world would feel if time flowed differently. If broken objects repaired themselves, if heat concentrated rather than dispersed, if memories formed backward, the entire structure of experience would collapse. You wouldn't be able to function. You wouldn't recognize patterns. You wouldn't detect cause and effect. Life depends not just on the existence of time, but on its direction. The consistency of that direction allows biological processes to unfold in reliable sequences. DNA replicates, cells divide, organisms grow, sensory systems respond. All of these require irreversible steps. When you consider these ideas gently, the question of whether time once flowed backward becomes easier to answer. Not in the literal sense, not in the sense of everyday events reversing themselves, but in the sense that the earliest universe did not yet supply the conditions required for direction to exist. Before the gradients formed, before entropy had room to grow, time had no arrow. The forward progression you experience emerged only after the universe began to evolve away from its earlier state. If the possibility of reverse time doesn't exist in physical reality as we know it, but the emergence of direction does, then the next natural question becomes how the laws of physics themselves relate to this direction. When you look closely at the way the world behaves, it becomes clear that time moves forward in your everyday experience. You see things age, break, cool, scatter, settle, and transform in ways that never reverse on their own. That direction feels so natural that it's easy to assume the laws of physics must contain some rule that enforces it. You might imagine that somewhere in the equations describing motion, energy, or force, there is a line that says events must unfold from past to future. But once you start studying those laws, something surprising emerges. Most of them don't specify any direction at all. They work just as well if you reverse time as they do if you let it run forward. This creates an interesting puzzle. If the underlying rules don't care about direction, then why does your experience show such a strong sense of forward motion? To explore this gently, it helps to think about motion in its simplest form. Take a ball rolling across a smooth floor. If you filmed that motion and played it forward, the ball would roll normally. If you filmed the same motion and played it backward, the ball would appear to roll in the opposite direction, returning to its starting point. The physics equations describing the ball's motion don't object to either version. They work the same way in both directions. The ball's path might not be typical in reverse, but nothing in the mathematics prevents it. The only thing that distinguishes the forward direction from the backward one in real life is friction, which spreads energy into the environment. That spreading is what gives the forward direction its specialness, not the underlying rules. When you look at Newton's laws of motion, they simply describe how objects respond to forces. They don't say that forces must push things from earlier moments into later ones. The equations allow you to plug in negative time just as easily as positive time. If someone were to reverse every velocity and every force in a system, the equations would track the reverse situation perfectly. The laws treat both directions equally. This is a key part of understanding why time's arrow isn't a built-in feature of the laws themselves. It emerges from how systems behave collectively, not from the rules guiding individual motions. The same idea appears when examining the laws of electricity and magnetism. These laws describe how electric and magnetic fields interact, how charges produce forces, and how energy moves through systems, but they don't enforce a direction. If you were to reverse the motion of every particle in a closed system, the equations of electromagnetism would continue to describe the reverse situation without contradiction. This means that the direction you experience isn't determined by the laws governing forces and fields. It's determined by the way real systems unfold from their starting conditions. Even quantum mechanics, which often feels mysterious, follows this same pattern. The equations describing how quantum states evolve work equally well forward or backward in time. They don't prefer one direction. They don't require a distinction between past and future. If you reverse the sign of time in the Schrödinger equation, it still holds. That symmetry is built into the structure of quantum theory. In fact, many quantum interactions behave as though time could run either way without affecting the outcome. That might feel counterintuitive because your experience of time is so strongly directional, but that feeling doesn't come from the laws, it comes from something else. It becomes helpful to pause here and consider what that something else might be. If the laws aren't imposing direction, then the direction must come from the conditions in which those laws operate. That realization shifts the focus from the laws themselves to the states they describe. While the rules allow motion in any direction, the world doesn't begin in a state where reversed motion is likely. The universe starts in a condition where entropy is low, and because higher entropy states are more probable, the system evolves in only one direction. The laws allow the reverse, but the initial conditions do not. This distinction is subtle but crucial. you can see an analogy in something familiar. Imagine shuffling a deck of cards. If the deck starts completely ordered, separated by suits and arranged by value, then almost every shuffle increases its disorder. The rules of shuffling don't forbid the deck from becoming ordered again, they allow any arrangement. But because the number of ordered arrangements is so tiny compared to the number of disordered ones, a random shuffle will never restore the original pattern. The rules don't prevent it, the conditions make it improbable. The same reasoning applies to time. When people first learn that the laws of physics don't care about direction, they often wonder why the world doesn't behave in reverse more often. The answer lies in the difference between what the laws allow and what actually happens. The laws of nature permit many possibilities, but only some of those possibilities occur with any frequency. Processes that reduce entropy don't violate the rules. They simply have such low probability that the universe never experiences them. You could spend a lifetime waiting for a broken egg to reassemble, and the laws wouldn't forbid it. The probability is so small, however, that it won't happen. There is another aspect of physical laws that helps explain why direction doesn't appear in the equations. Most fundamental laws describe relationships between quantities like energy, momentum, charge, and position. These relationships must hold regardless of when you evaluate them. If the laws favoured one direction of time, they wouldn't treat different moments equally, and that would break a deep symmetry of nature. The laws are built to be broadly applicable, covering everything from early cosmic conditions to everyday events. Direction arises not from the equations but from how the world begins and evolves. If you think about collisions between particles, the same idea appears. When two particles bounce off one another, the equations describing their motion don't prefer forward or backward time. If you reversed the velocities at the end of the collision, the system would retrace its steps perfectly. That reverse path is allowed by the laws. You simply don't see it because in any real environment, microscopic interactions quickly spread energy outward. Once energy disperses, the system drifts into states with far more possible arrangements, and the reverse trajectory becomes impossible to recreate without enormous precision. This lack of direction in the underlying rules helps explain why physicists often say that time's arrow is not a fundamental property of the laws, but an emergent property of the universe. Emergent properties come from how large systems behave collectively, not from the details of the equations themselves. The laws may be symmetric, but the world is not. The starting conditions break the symmetry, and once that happens, the forward direction becomes dominant. You can find similar symmetry in the laws describing gravity. Newton's law of gravitation and Einstein's equations of general relativity allow motion in either time direction. Nothing in those equations says gravity must act only in forward time. Mass curves, space-time, objects move along geodesics, and systems evolve according to gravitational interactions, but none of that depends on whether time is flowing from past to future or future to past. The laws would be just as comfortable describing reversed motion if the conditions allowed it, but they don't. Once again, the distinction comes down to how the universe was arranged at the beginning. The early universe was smooth, uniform, and low in gravitational entropy. This gave gravity room to create structure. That evolution produced stars, galaxies, planets, and everything else. And as structure increased, entropy rose. This rise defined the arrow of time. Gravity didn't force direction, it simply participated in the natural progression created by the initial low entropy state. It's also worth considering how randomness plays a role. When you think of random motion, you might picture something directionless. But random processes still tend to move toward higher entropy because there are more high entropy states available. Randomness itself doesn't break the symmetry of the laws. It simply reinforces the statistical tendencies built into the universe's configuration. Even random motion leads to irreversibility because the conditions favour spreading, dispersing and mixing rather than concentrating and unmixing. You might ask whether there are any laws that care about direction. There is a type of particle interaction called the weak force that does break time symmetry under certain conditions. But this asymmetry is incredibly small and subtle. It doesn't influence the large-scale behaviour of entropy in any noticeable way. So while time symmetry is not perfect at the deepest levels, the slight asymmetry in the weak force does not create the arrow of time you experience. That arrow still arises from entropy, not from the laws themselves. One way to understand this is to imagine a perfect billiard table, with balls arranged in a tight formation. If someone strikes them, they scatter. If you filmed the event and played it backward, the balls would appear to gather into a perfect formation and leave one ball rolling backward to the cue. The laws would allow both versions. The reverse version looks unnatural not because it violates the rules, but because it would require precise coordination among all the balls. Any slight deviation would prevent the reversed version from occurring. In a real environment, tiny influences, air currents, imperfections, thermal vibrations, push the system toward the scattered state. The direction comes from the conditions, not the rules. There is something grounding about realizing that the laws of physics don't need to encode direction for you to experience it. They set the stage. The condition of the universe sets the movement, and the combination of both determines what you observe. Because the laws are symmetric, they can describe worlds different from ours, hypothetical scenarios where direction might emerge differently. But in the world you inhabit, the starting point ensured that entropy would rise, and because of that, time gained its direction. This understanding helps clarify that the forward flow you experience is not something imposed from outside. It's the outcome of the universe's initial state interacting with laws that are neutral about direction. Once you see this neutrality, the arrow of time becomes less of a mysterious cosmic feature and more of a natural result of how systems evolve. The consistency of the arrow doesn't come from the equations. It comes from the fact that all the systems those equations describe begin in conditions that make forward evolution overwhelmingly likely. When you think about why the world grows more disordered over time, it's tempting to imagine some force pushing everything toward messiness. It can feel that way when a tidy room becomes cluttered, or when fresh food goes stale, or when a perfect arrangement of objects gradually drifts apart. But the more you explore the idea, the clearer it becomes that nothing is actively nudging things into chaos. Instead, the direction you see around you comes from something more subtle, something that sits underneath the details of every event. Probability is the quiet guide shaping the way systems evolve. It doesn't shout. It doesn't impose rules. It simply sets the landscape in which all processes unfold, and that landscape favours states that are easier to reach. Because messy states are easier to reach than tidy ones, the world appears to move toward disorder. To get a sense of how this works, imagine you have a box filled with two kinds of balls, some red and some blue, all mixed together. If you close the box and shake it, the mixture becomes even more jumbled. If you're lucky, one shake might separate a few colours, but the odds overwhelmingly favour mixing. Now imagine trying to return the balls to a perfectly sorted arrangement through random shaking alone. You could shake the box countless times, but you would almost never see the colours separate back into perfect order. The reason has nothing to do with shaking in one direction versus another. It has everything to do with how many mixed states exist compared to sorted ones. There are far more ways for the balls to be jumbled than for them to be neatly arranged. So when you shake the box, you aren't pushing it toward disorder. You're just allowing it to explore the possibilities. Most of those possibilities look messy. This simple idea extends to nearly every process you observe. When milk mixes into coffee, the combined liquid has vastly more possible arrangements than the separated liquids. When perfume spreads through a room, the dispersed molecules have countless configurations compared to the tiny number of configurations where the scent remains concentrated near the bottle. When heat spreads from a warm object to a cooler one, the more uniform temperature represents a state with many more micro-level arrangements than the concentrated heat did. Each of these changes is guided not by force but by probability. The direction comes from the number of ways things can arrange themselves. It becomes easier to see this if you examine a system at a microscopic level. At any moment, every particle in a material is moving. Some move faster, some slower, some collide, some drift. Because there are so many of them, their collective behavior appears random, but that randomness tends to push the system toward more probable states. For example, if you have all the air molecules in a room starting in one corner, their random motions will quickly spread them out. The reverse, where random motions gather all the molecules back into the corner, is technically possible, but so improbable that it effectively never happens. The difference between these two possibilities explains the direction you experience as the passage of time. Consider how heat spreads through an object. At first, there may be an uneven distribution, with one region much hotter than another. The particles in the hot region move more quickly, transferring energy to nearby particles. Over time, the differences even out. The final state, where the temperature is uniform, has many more possible particle arrangements. Each particle can move at slightly different speeds, interacting in countless ways. The initial ordered state had fewer possible arrangements because the speeds were more concentrated. The spread toward uniformity reflects probability taking over, creating a natural direction for the system to follow. This might also help explain why certain tasks feel easier than others. Putting books back on a shelf in an exact sequence requires careful attention. Many steps must align correctly. But letting them become slightly disordered requires no attention at all. The messy state doesn't demand precision because there are so many arrangements that fit under the category of messy. You don't have to do anything for the disorder to appear. It emerges naturally because the probability of ending up in a messy state is much higher than the probability of returning to a precise arrangement. Thinking about probability in this way can make many common experiences feel less frustrating. While it might seem like the universe has something against your efforts to keep things organized, what you're really dealing with is the overwhelming ratio of disordered states to ordered ones. When you straighten a room, you create a highly specific arrangement. Every object is placed with intention. But once you resume living in that space, each movement, each use, each shift increases the chance that objects drift into one of the many disordered states available to them. No special force is behind it. The imbalance between the number of tidy and untidy states explains the difference. You can also apply this idea to more complex systems. Consider how a river carves its path. The flowing water encounters rocks, soil, and sediment. Each particle it carries can settle in countless locations. Over time, small variations build on one another, and new patterns emerge. Even though each grain's movement seems unpredictable, the overall behavior follows a path shaped by probability. Water is more likely to spread sediment into broader areas than to stack it into narrow towers. That's why erosion creates wide valleys rather than impossibly precise formations. A similar principle applies to weather. Individual air molecules move chaotically, yet the weather trends they produce follow predictable patterns. Warm air rises, cold air sinks, moisture condenses according to temperature. These general behaviors arise from countless micro-level interactions shaped by probability. There is no need for a master force pushing systems toward disorder. The natural imbalance between the number of possible mixed states and ordered ones guides the evolution. Even your own thoughts are influenced by probability. When neurons fire, they create networks of activity that reflect patterns you've learned. Some connections strengthen because they've been used often. Others fade because they haven't. The brain doesn't maintain complete order or complete chaos. It drifts towards states that strike a balance between stability and flexibility. The pathways that form depend on which patterns are most likely given your experiences. Probability guides these changes in much the same way it guides how sugar dissolves, how heat spreads, or how gases mix. It might feel unsettling to realize how much of the world's behavior stems from probability rather than strict rules. But in practice, this actually provides stability. If systems followed only rigid rules, they wouldn't be able to respond flexibly to small changes. They would behave the same way every time, regardless of environment. The world you live in is shaped by systems that are sensitive to initial conditions but still follow predictable trends. Probability smooths out the details, allowing large-scale patterns to emerge even when individual events appear unpredictable. Let's look at a larger example that might seem far removed from everyday life, but follows the same principles. Think about the formation of galaxies. In the early universe, small variations in density allowed gravity to pull matter into clusters. These clusters grew because it was more probable for matter to gather in regions where other matter had already begun to accumulate. Gravity amplified the initial fluctuations, but probability guided the process. There were many more possible arrangements in which dense regions became denser than in which they spread out evenly again. Even on cosmic scales, the march toward messiness is guided by probability, though in this case the messiness creates structure rather than destroying it. The variety of possible arrangements grows as structures form and evolve. The arrow of time appears in the process because the number of accessible states increases. Probability also explains why certain events are effectively irreversible. When you break an egg, you create a system with an enormous number of possible arrangements. The pieces of shell, the spreading liquid, the microscopic textures of the surface, all of these details create configurations that have an astronomically larger count than the original unbroken egg. For the egg to reassemble, every particle would have to find its way back to a limited set of arrangements. Even though the laws of physics allow it, the probability is so vanishingly small that you would never see it happen. This isn't because messy states are forbidden from reversing. It's because the number of tidy states is tiny compared to the number of messy ones. Probability also plays a role in how systems respond to small disturbances. If a neatly arranged display of objects on a table receives even a slight nudge, the disturbance introduces uncertainty. Each object has many more ways to be a little out of place than to remain in perfect alignment. The disturbance doesn't need to be dramatic. A small vibration or shift is enough to send the system drifting toward a slightly more disordered configuration. Over time, these tiny shifts accumulate, making the ordered state hard to maintain. You might straighten things again, but the effort you put into that is another example of imposing order on a system that naturally prefers a large space of possibilities. This doesn't mean messy states are always visually chaotic. Sometimes a messy state looks organized on the surface because the system has many ways to appear that way. A pile of leaves may take on a roughly rounded shape, but the internal arrangement is complicated and variable. That appearance hides countless configurations that all fall under the same broad category. Meanwhile, a neatly raked arrangement of leaves represents only a tiny fraction of possible configurations. Probability favors the pile over the neat arrangement unless someone intervenes. Intervention is an important concept, because humans often work against the natural tendencies of probability. When you clean, organize, sort, or repair something, you're intentionally guiding the system into a narrow region of its possible states. You're doing work to reduce entropy temporarily, but the moment you stop maintaining that order, the system begins to relax back into its more probable configurations. This relaxation is not a collapse into chaos, but a return to the broad landscape of possibilities that exist without constraint. You might find it interesting to realize that probability not only shapes physical systems, but also shapes social ones. Consider a group of people trying to maintain a perfectly synchronized schedule. It's possible, but it requires constant effort. A single unexpected event, traffic, illness, miscommunication, creates variations that ripple outward. There are more ways for the schedule to become disorganized than to remain perfectly aligned. The shift toward disorder happens naturally unless people continually impose structure. Once again, probability is guiding the evolution. Understanding probability as the engine behind time's arrow can make the direction feel less mysterious. You no longer need to imagine a force pushing the universe toward disorder. You only need to imagine a landscape where most of the paths lead into messier territory. The world moves toward disorder because disorder is the region of possibility that occupies almost the entire landscape. The ordered states sit in tiny islands that require effort to reach, and even more effort to maintain. Letting this idea settle makes it clearer why time feels irreversible. You experience the forward direction, because events move from the unlikely toward the likely. You don't see the reverse because the probability is too low to matter. Once that connection takes root in your understanding, the arrow of time becomes easier to grasp. It isn't imposed, it emerges. It can be difficult to picture a world without disorder because everything you interact with carries some level of unpredictability. A piece of fruit ripens and then softens. A warm drink cools on the table. Dust accumulates. Clothing wrinkles. Floors show signs of traffic. None of these changes require your permission. They simply happen as part of the way systems evolve. But you can learn a lot about the nature of time by imagining what would happen if disorder did not appear, or if entropy had no room to increase. Thinking about a perfectly ordered world may feel unusual at first, but the idea helps reveal what time would look like in a universe where the arrow you experience did not exist. To begin, imagine a space where everything is arranged in a state of complete uniformity. There are no temperature differences, no density variations, no clusters or gaps. Every particle is positioned in a way that is perfectly symmetrical with every other. If you were to zoom into the smallest level, each particle would have the same energy, the same spacing, the same orientation. Nothing would drift, mix, or spread, because there would be no reason for anything to behave differently from anything else. The system would have no gradients to follow, no directions in which to evolve. In such a world, time would lose the familiar structure it has in your everyday experience. When you look around a real room, the differences between one object and another help you understand what moment you're in. You recognize that a fresh cup of tea marks an earlier moment, and a cooled cup marks a later one. You know that a footprint in snow indicates a more recent event than untouched snow. You rely on these contrasts to sense before and after. But in a perfectly ordered world, every moment would look the same. You wouldn't have a way to distinguish one point in time from another because nothing would change. If you focus on that idea slowly, it becomes clearer just how deeply your understanding of time depends on change. You know time is passing because you notice processes unfolding. You see motion. You feel heat transferring. You hear sounds fading. You watch objects shift position. You observe your own thoughts move from one idea to another. In a perfectly ordered world, none of these processes would occur. Without gradients, there would be no reason for energy to flow or for matter to rearrange itself. Without rearrangements, there would be no cause-effect sequences. Without sequences, the idea of past and future would lose meaning. You can think of this in a simple way by imagining a perfectly level playing field with no hills or valleys. If you placed a ball on this surface, it would not roll because there would be no direction for it to move. In your everyday world, uneven ground gives the ball a preferred path. In a perfectly ordered universe, the ground would be level in every possible direction. The ball would remain exactly where you placed it, and the universe would remain exactly where it began. Without gradients, motion would not have a preferred path. Without preferred paths, direction becomes irrelevant. Now imagine trying to perform even the simplest action in a perfectly ordered world. Suppose you attempted to heat part of a surface. In the real world, heat would spread outward from the warm spot until it reached an even distribution. But in a perfectly ordered world, the moment you introduced heat, the system would no longer be perfectly ordered. So the scenario cannot occur. Any attempt to change part of the system would introduce a gradient which contradicts the premise of perfect order. That means no processes could begin at all. No reactions, no spreading, no mixing, no evolution. A perfectly ordered world would not allow the first step of any sequence to happen. This reveals something important. Time as you know it depends on the ability of systems to change. Not just visible change, but microscopic change that spreads across particles and structures. If change is impossible, time becomes an empty concept. You might still define time as a coordinate in an equation, the way physicists talk about t in formulas, But that coordinate would do no work. It would add nothing to your understanding because no moment would differ from any other. Without entropy increasing, the arrow of time would never develop. This doesn't mean time would reverse. It means time would not have direction at all. It would feel similar to a frozen scene in which events have no progression. Past, present, and future would not differ. If you were a conscious observer inside such a world, you would never notice yourself aging. You would never notice anything aging. There would be no marks, no traces, no developments. Memory itself could not exist because memory requires physical changes in the brain. But physical changes are impossible in perfect order. Without memory, you could not form a sense of yourself. Without a sense of yourself, there would be no experience of time. You can picture this more concretely by comparing it to familiar situations. Think of how you identify the difference between morning and evening. Light shifts, temperatures change, activity rises or falls, your routines unfold in order. A perfectly ordered world would remove every one of these cues. Nothing would brighten or dim, nothing would warm or cool. No one could perform any routine because performing a routine requires actions that alter the state of the world. Even your heartbeat depends on change. Muscles contract, cells transmit signals, ion channels open and close. All of that depends on motion and gradients. In a perfectly ordered universe, these processes would never start. This leads to another important idea. If nothing can happen, there is no way to define before and after. A sequence of zero events gives you no method for identifying direction. In such a setting, the concept of time is not reversed or frozen by force. It simply ceases to have operational meaning. Time becomes like a label you no longer use because nothing responds to it. You can think of it as trying to measure distance in a world where everything occupies the same point. The unit of measurement becomes irrelevant. Another layer appears when you think about how structured real systems are. Your world always contains gradients, warm surfaces touching cooler surfaces, liquids mixing, forces pulling objects downward, chemical reactions releasing heat, biological systems consuming energy. These gradients give direction meaning. You know that something is happening because the gradients smooth out over time. The smoothing is what creates the sense of forward motion. Without differences to smooth out, time would not move. The very existence of life depends on the universe not being perfectly ordered. Biological systems rely on energy flowing from regions of high concentration to regions of lower concentration. When you eat food, your body extracts usable energy from it and releases waste energy into the surrounding environment. This process only works because the universe allows entropy to increase. A perfectly ordered universe would not support life because it would not allow the energy transfers that biological systems depend on. Even basic metabolism would be impossible. This also helps explain why the early universe, despite being extremely hot and energetic, still counted as low entropy. It was ordered in a specific sense, gravitationally smooth, uniform and lacking structure. Because it was so uniform, it had the potential for entropy to rise dramatically. Once the universe began to expand, slight fluctuations in density created opportunities for structure to form. Those structures allowed energy to flow, reactions to occur, and systems to evolve. That evolution is what made time's direction show up. Without the potential for entropy to increase, the universe would have stayed in that initial uniform state indefinitely. It may feel strange to think of order as limiting and disorder as creating opportunity, but that is how entropy works. Low entropy states have few possible configurations. That means they have limited ways to evolve. High entropy states have many possible configurations. That means they support a broad range of processes. A perfectly ordered world has no direction because it has nowhere to go. A world with disorder has direction because it contains countless ways to transform. You can see a gentle version of this idea in your daily routine. Imagine a shelf with books arranged alphabetically. There are few arrangements that preserve the alphabet. But once a few books are out of place, there are many ways they can remain out of place. The disorder allows new configurations, new possibilities, and new paths for the shelf to take. Without disorder, the shelf remains frozen. With disorder, it evolves. Thinking about this slowly shows how deeply time is tied to the potential for change. If a system has no potential to change, time does not move in a meaningful way. If a system has many paths it can follow, time moves forward as the system explores those paths. The more complex the system, the more directions it can take, and the more evident the arrow of time becomes. A perfectly ordered world would not only remove physical change, it would remove meaning. Meaning requires contrast. You recognize significance because events differ from one another. You learn because earlier states give way to new states. You remember because your brain changes. You understand time because those changes accumulate. Remove the changes and everything becomes static. Meaning depends on the arrow of time. There's also something reassuring about realizing that your world is not perfectly ordered. The messiness that surrounds you, the incomplete tasks, the shifting conditions, the items out of place, reflects the very property that makes experience possible. Without that messiness, nothing would happen. The world would be silent, motionless, and devoid of the dynamics that allow life to unfold. Imperfection is not a flaw. It is a requirement for time. When you think about this calmly, you might start to see the familiar arrow of time not as a constraint, but as an enabling condition. It allows stories to develop, relationships to evolve, and memories to form. It creates a sense of continuity that lets you understand who you are and how you arrived here. A perfectly ordered world would remove all of that. The absence of disorder would erase direction, and the absence of direction would erase experience. If perfect order removes the arrow of time, then the opposite question naturally arises. Does time lead toward a future that is already fixed, or is the future open and shaped by the same irreversible processes we've been examining? When you think about time moving forward, it's natural to wonder whether that forward motion is carrying you towards something fixed or something still developing. People often ask if the future is already there, laid out in detail, waiting for you to arrive. Other times they imagine the future as something flexible, shaped by each action you take. This question reaches into the heart of what direction in time really means. You can feel the pull of tomorrow, but you cannot step into it early or observe it ahead of schedule. All you have are patterns from the past, choices you make now, and expectations built from both. The idea that the future is either written or unwritten invites you to examine what the arrow of time tells you about how the universe unfolds. One of the reasons this question feels complicated is that your mind naturally tries to build predictions. When you sense a pattern, you expect it to continue. If you hear storm clouds overhead, you anticipate rain. If you place bread in the toaster, you anticipate heat darkening the surface. These predictions make it feel as though the future is a kind of extension of the past. You picture what will happen next using everything you've learned. But memory and prediction are not the same as certainty. They are tools shaped by experience. They rely on patterns that have held up so far, not on knowledge of a predetermined outcome. Physics gives you another way to consider the question. Many of the laws that describe how the world works allow you to calculate what could happen under certain conditions. For simple systems, such as a ball tossed into the air, you can predict its path very accurately. The equations give you precise answers because the system is orderly and the variables are few. But as soon as you shift into systems with many interacting parts, predictions become harder. Even if the laws allow you to compute outcomes in theory, the complexity grows so quickly that in practice, you cannot use exact predictions to map the entire future. Think about something as mundane as the weather. The atmosphere follows definite physical rules, but slight variations in temperature, humidity, wind, and pressure create branching possibilities. A tiny change in one location can influence events elsewhere. Because the atmosphere contains enormous numbers of interacting molecules, You cannot track them all. The laws do not fail. The complexity simply outruns your ability to predict. This doesn't mean the future weather is predetermined in a way you could uncover if you had more information. It means that while the laws govern the process, the unfolding remains sensitive to small variations that lead to many possible outcomes. This sensitivity raises the question of whether uncertainty is built into the universe, or whether it arises only because your knowledge is limited. Quantum mechanics offers one perspective. In the quantum world, outcomes are probabilistic. A particle might exist in multiple possible states until a measurement occurs. The laws give you probabilities, not certainties. You know what might happen, but not what must happen. Even if you had access to every detail of a system, the theory still gives you a range of possible futures rather than a single predetermined one. This suggests that the future, at least at the smaller scales, does not exist in a fixed state waiting to be revealed. But the world you experience isn't limited to particles or weather systems. Your life unfolds through choices. You decide what to say next, where to go, how to respond to someone, or which direction to take when faced with uncertainty. These choices feel like genuine contributions to shaping what happens. If the future were already written, your sense of choosing might seem like an illusion. Yet your choices depend on internal states that develop through memories, experiences, habits, and values. Those internal states are shaped by irreversible processes in the brain, driven by the same arrow of time that governs everything else. To understand how the arrow of time affects this question, it helps to look at how events are structured. The past contains fixed records, memories, photographs, fossil traces, worn surfaces. These records are physical changes that cannot be undone. The present contains ongoing processes, chemical reactions, neuronal firings, mechanical interactions. These processes respond to the past but are not bound to a single future. The future contains possibilities, paths that could unfold depending on how events interact. Nothing in this structure suggests that the future exists in the same way the past does. The past leaves traces. The future leaves none. If you picture the universe as a system evolving from a low entropy beginning, the direction of time reflects the growth of complexity and the increase of accessible states. The universe started with a narrow range of configurations. As time moves forward, the number of possible configurations expands. Systems develop more branching paths rather than fewer. This expansion of possibilities suggests that the future cannot be compressed into a single predetermined story. The number of potential arrangements grows constantly, and each irreversible process contributes to that growth. If the future were fixed, you would expect the number of possible states to shrink or stay constant. But the opposite happens. Another way to look at this is by considering how information spreads. When a process occurs, information about the event becomes embedded in the world. A footprint forms in the sand. Heat diffuses across a surface. A chemical reaction produces new molecules. Each of these outcomes increases the number of informational traces in the environment. This increase reflects entropy rising. As entropy rises, the system gains more flexibility. More configurations become possible. Each new moment has more potential directions than the one before it. That steady expansion of possibilities suggests that the future is shaped moment by moment, rather than written in advance. You can notice this in your own life. Imagine thinking back to how you understood the world years ago. The possibilities you considered then were shaped by your experiences at that time. Since then, you've learned more. Your circumstances have changed. You've met new people. You've seen new places. These accumulated experiences expanded your sense of what could happen. The future you imagined long ago likely looks different from the future you imagine now. If the future had been fixed all along, these shifts in perspective would not matter. But they do matter. They reveal that your sense of what is possible changes because the world around you continues to evolve in one direction. Another point worth considering is that irreversible processes generate unpredictability. When heat flows from a warm object to a cooler one, the microscopic motion of particles becomes increasingly varied. When you mix ingredients, their interactions produce complex outcomes. When a leaf falls, tiny air currents affect the motion, and each disturbance multiplies the number of possible paths. These processes create details that no observer could track perfectly. The future becomes unknowable not because it is predetermined, but because the universe explores a vast landscape of possibilities as entropy rises. This doesn't mean the future is completely open at every level. Certain events follow stable patterns. A dropped object falls, a car engine produces heat, a candle flame grows dim as fuel is consumed. These patterns give you confidence in many aspects of life. The laws of physics provide predictability where conditions are simple. But predictability does not require predetermination. It requires consistency. The laws are consistent. The outcomes vary depending on the environment, the initial conditions, and the interactions along the way. If the question is whether the future exists in the same way the past does, the evidence leans toward no. The past is filled with fixed states that you can examine. The future contains none. This absence of traces is not a small detail. It is a defining feature of the arrow of time. A fixed future would generate records just as a fixed past does. Those records would already be embedded in the world around you. Instead, the world contains only traces of what has already occurred. Nothing carries physical marks of what has not yet happened. It becomes even clearer when you think about memory. You remember the past because events leave structural changes in your brain. You cannot remember the future because it leaves no traces. If the future were already written, your mind would encounter signs of it in the same way it encounters signs of the past, but it does not. Everything about your mental life reflects a symmetry. Information flows from past to future, not from future to past. That asymmetry does not depend on whether you feel in control of your decisions. It arises from the physical processes behind memory, perception, learning, and growth. Your brain functions by constantly updating itself. This updating process cannot reverse. The physics of neurons relies on chemical gradients and irreversible reactions. Because these reactions only proceed in one direction, the mind can only absorb information from earlier moments, not from later ones. This aligns perfectly with the idea that the future is not fixed but generated as events unfold. Some philosophical perspectives imagine a universe in which the entire timeline exists all at once, with past, present, and future all equally real. In such a picture, time resembles a dimension like space. The experience of flowing from moment to moment would be similar to moving along a path. But even in such a framework, the arrow of entropy would still determine the direction of experience. You would still remember only the earlier segments. You would still observe irreversible processes. Your conscious experience would still unfold from lower entropy to higher entropy. The future, though it might exist abstractly in such a picture, would still feel unwritten because your mind experiences only the forward unfolding. But if you remain grounded in physical evidence rather than philosophical interpretation, the simplest explanation is that the future has not happened yet. It exists only as a range of possibilities shaped by the present. As time moves forward, those possibilities narrow into actual events, and those events become fixed records. The process mirrors how a tree grows. The trunk may shape the direction of growth, but the branches develop through countless small influences. The final shape is not predetermined but emerges as the tree responds to its environment. In this sense, the arrow of time is the unfolding of potentials, not the execution of a script. Each irreversible process contributes to the formation of new conditions. Each new condition creates new possibilities. Each choice you make alters the path ahead. The future is not written because it has not had the opportunity to form its traces yet. It is still in the making, shaped by the probabilistic evolution of the universe and the irreversible processes that define time's direction. Letting this idea settle can bring a sense of openness. the direction of time does not push you toward a destination that has already been constructed. It guides you through a landscape where new features emerge as you move. You follow a path that did not exist until you stepped onto it, and each moment adds something new to the world, something that was not guaranteed, something that becomes part of the past only after it happens. If you've ever tried to understand why time feels like it only moves forward, you eventually reach a point where everyday examples, even the familiar discussions of entropy, begin to feel incomplete. They explain how the world evolves, why messiness grows, why memories form, and why processes don't naturally reverse. But they don't explain why, at the smallest scale, nature allows certain possibilities and blocks others from ever appearing in your experience. To understand that deeper layer, you must look closely at quantum mechanics, the framework that describes how particles behave at the smallest scales. Even though quantum mechanics often feels disconnected from daily life, it quietly influences every part of the forward drift you experience. Time's arrow appears strongest at scales where classical behavior emerges, yet the clues that hint at why the arrow exists in the first place are woven deeply into quantum behavior. The first thing that stands out when you explore the quantum world is how different it feels from the world you know. Instead of objects having precise locations and exact motions, particles exist in states described by probabilities. Instead of events unfolding in strict sequences, possibilities overlap until something interacts with them. This difference doesn't break the arrow of time, but it shows that the arrow isn't something imposed by the smallest components of nature. The fundamental equations work whether time runs forward or backward. That symmetry makes the emergence of direction even more curious, because the world you observe shows a clear, unmistakable flow. Even though the equations allow motion in either direction, the way quantum processes actually unfold gives hints about why you never see reverse events. The clue lies in how quantum states interact with their surroundings. A particle on its own can behave in ways that seem reversible. Its wave function spreads out, evolves smoothly, and doesn't show any preference for direction. But the moment the particle interacts with something else, another particle, a wall, a photon, the process becomes irreversible. This irreversibility doesn't appear in the equations themselves. It appears in how information spreads. To get a simple sense of this, imagine a particle that starts in one location. Its wave function spreads over time, meaning the particle has a range of possible positions it could occupy. As long as the particle doesn't interact with anything, this spreading can reverse. But in the real world, particles never exist in perfect isolation. They collide, scatter, absorb, emit, or latch onto something. Each interaction leaves a trace of information in the environment. Once information spreads out, the original state cannot be reconstructed. Theoretical reversibility collapses, replaced by practical irreversibility. This idea becomes clearer when you think about something familiar, a single drop of dye dispersing in water. At a fundamental level, there's nothing forbidding the dye molecules from reassembling into the original drop. But once the dye has spread throughout the water, its molecules have interacted with countless water molecules. Every collision has exchanged information. The water now holds traces of the dye's path in the microscopic motions of its molecules. To reverse the spreading, you would need to reverse every single interaction. The mathematical laws allow it. The universe does not supply the conditions required for it. The quantum version of this example involves something known as decoherence. Decoherence describes how quantum states lose their ability to behave in purely quantum ways once they interact with many other particles. Before decoherence, a system can exist in multiple overlapping possibilities. After decoherence, those possibilities collapse into classical outcomes. Decoherence happens incredibly fast for macroscopic systems. A dust particle floating in a beam of sunlight decoheres in an unimaginably short time because it interacts with countless photons. Once decoherence has occurred, reversing the process becomes impossible because the required information has dispersed beyond retrieval. It's important to pause here and notice that decoherence does not add a direction to the laws of physics. It only describes how interactions unfold in systems that are not completely isolated. The forward drift you experience arises because these interactions always disperse information rather than gather it. The dispersal aligns naturally with entropy increasing. This is one of the quiet ways quantum mechanics contributes to the arrow of time. Not by forcing direction, but by ensuring that once information leaks into the environment, the system cannot return to its earlier state. Another quantum clue appears when you consider measurement. In classical physics, observing something doesn't change its state. You can watch a pendulum swing without altering its motion. You can track a planet without influencing its orbit. But in the quantum world, measurements involve interactions. These interactions change the system in irreversible ways. When you measure the position of a particle, you collapse its wave function into a specific value. This collapse isn't something the fundamental equations enforce. It emerges from the interaction between the system and the measuring device. The act of measurement disperses information, creating an irreversible mark. That irreversible mark becomes a step in the forward progression of time. If you think of memory as a form of measurement, this connection becomes even clearer. When your brain records an experience, neurons fire, chemicals move, and pathways strengthen. Each of these changes reflects irreversible processes. You cannot measure something without leaving a trace. You cannot form a memory without altering your physical state. These small irreversibilities accumulate into the directional sense you experience. Another clue appears in quantum entanglement. Entangled particles share a connection that allows their states to be correlated even when separated by large distances. But once entangled states interact with their surroundings, those correlations become spread out and diluted. The environment picks up faint traces of the entangled information, causing decoherence. The entanglement breaks down. The loss of coherence reinforces the arrow of time because reversing the entanglement would require reversing every interaction in the system and the environment. Once again, the laws allow reversibility in theory, but the world you inhabit never provides the conditions required for reversal. This means the arrow of time is not something that appears out of nowhere. It emerges from the way quantum systems interact with their environments. As soon as systems become large enough to have many interactions, which happens almost immediately for anything composed of many particles, reversal becomes practically impossible. The world begins behaving in a classical way, where entropy increases and time has a direction. You can see this transition by imagining a simple scenario involving a small particle and a large environment. Suppose the particle begins in a precise quantum state. Over time, it interacts with surrounding particles. Those interactions cause the environment to hold information about the particle's history. To reverse the arrow, you would need to remove that information from every part of the environment. Even if you could reverse the particle's path, the environment would still contain traces of what happened. Those traces prevent full reversal. The arrow of time emerges from the inability to erase these traces. If you expand this idea to larger systems, such as a group of particles interacting inside a warm gas, the picture becomes even more dramatic. The interactions are constant and numerous. Information spreads almost instantly. Even though the underlying equations allow the gas to move from a disordered state back into an ordered one, the information dispersal is so rapid that reversal doesn't occur. The arrow of time becomes locked in because information moves outward from small scales to large ones. That outward movement defines the direction you perceive as forward. The presence of probability also plays a deeper role in this story. In quantum mechanics, outcomes are not fixed until interactions occur. The laws give probabilities for different outcomes. These probabilities reflect the possible paths a system can take. Once an interaction occurs, the system selects one path and leaves behind traces of that choice. These traces become embedded in the world. The existence of these traces means the system cannot unfold backward. It cannot erase the interactions. The increasing number of traces aligns with entropy rising. Each new trace adds to the future's possibilities. Each new irreversible event adds another step in the forward drift. One interesting consequence of all this is that quantum mechanics doesn't contradict the arrow of time. It explains why the arrow exists. The laws allow reversible behavior, but the world imposes conditions that make reversal implode under the weight of complexity. The arrow of time doesn't emerge from the smallest equations. It emerges from how those equations behave when you have many particles, many interactions, and many opportunities for information to spread. You might think back to the idea of watching a film in reverse. A dropped glass reassembles, a splash coils inward, a flame unburns. Each reversal would require quantum states to align perfectly, reversing interactions that occurred at microscopic scales. Every molecular vibration, every scattered photon, every slight exchange of energy would need to unwind. Decoherence would need to reverse as well. The universe would have to gather information instead of dispersing it. That requirement contradicts what happens naturally. Quantum interactions always spread information. They never assemble it. This spreading is why time feels like it has a direction. Another helpful way to explore this is to think about the world as a collection of information channels. Each interaction transmits information from one part of the system to another. Some interactions spread information widely. Others do so in tiny, almost imperceptible ways. But once information begins to disperse, it cannot be unspread. The transmission creates a one-way path. This one-way path is not forced by the equations. It arises because interactions connect systems to larger environments, and environments contain too many degrees of freedom to manage reversibly. This is true for a glass breaking. It is true for a memory forming. It is true for every event that leaves a trace. This isn't just a conceptual idea. It shows up in experiments. Quantum systems behave differently when isolated. They retain coherence longer. They allow reversibility. But as soon as those systems touch the environment, even in a small way, their behavior becomes classical. The overlap of possibilities collapses. The forward drift appears. The arrow of time emerges naturally once isolation disappears. Thinking about quantum mechanics in this way might at first feel distant from ordinary experience, but it helps show how the familiar direction of time arises from a deeper structure. Every irreversible event you notice in daily life, melting ice, cooling tea, fading sound, reflects quantum interactions producing classical outcomes. Those classical outcomes carry traces of the past and none of the future. That asymmetry defines your sense of time. When you look up at the night sky and see the stars scattered across the darkness, it can be easy to forget that the entire universe is stretching, changing, and moving in ways that shape the passage of time itself. Most of the time, you go about your day without thinking about the expansion of the cosmos. You focus on simple things, like the warmth of sunlight on a window or the quiet sound of distant traffic. Yet the universe's growth plays a role in the direction of everything you experience. The large-scale structure of reality sets the backdrop against which the arrow of time unfolds. Understanding how expansion shapes this arrow offers another way of seeing why time feels as though it only moves forward and never loops back. To begin exploring this, it's helpful to picture the universe not as a static backdrop but as something dynamic. Space itself stretches. Galaxies drift apart. Light travelling through the cosmos becomes increasingly stretched as the space between its crests grows. This stretching, known as redshift, provides direct evidence of expansion. But expansion is more than an interesting astronomical detail. It sets the conditions under which entropy increases. Without expansion, the universe might have evolved very differently. The familiar arrow of time might not have emerged in the form you know. Imagine the universe when it was extremely young. Temperatures were extraordinarily high. Matter was packed tightly. Energy was distributed in nearly uniform ways. This uniformity meant the universe held a large amount of potential for entropy to grow. Expansion acted like a release valve, giving space room to develop structure. Without that room, the low entropy beginning could not have unfolded into the complex world you see now. The stretching of space allowed gravitational clumping, chemical complexity, and the formation of stars, planets, and eventually life. Every step of that complexity reflects an irreversible drift from a simple beginning toward more varied states. This doesn't mean expansion pushes time forward like a force. Instead, expansion creates the environment in which forward evolution naturally occurs. You see an expanding universe today because early conditions allowed it, and once expansion began, entropy had pathways to rise. The increase in entropy is what defines the arrow of time, but expansion made that increase possible on the scale of the cosmos. One way to visualize this is by imagining a large sheet being pulled outward from its edges. If dots are drawn on the sheet, the dots move apart as the sheet expands. Their separation isn't caused by the dots moving through space, but by space itself stretching. In a similar way, galaxies drift apart even though they might not be moving in the traditional sense. Expansion carries them. As space stretches, new configurations become possible. Regions that were once close enough to influence each other separate. Temperature gradients smooth out across larger distances. These shifts create direction because each newly expanded region holds more possible arrangements than before. If the universe were not expanding, it might eventually settle into a state where entropy could no longer rise. Without new space for matter and energy to spread into, systems would reach equilibrium. In such a world, time would not feel the way it does today. Processes would slow, complexity might not develop. The notion of a future distinct from the present would fade. Expansion keeps the universe from falling into this state prematurely. It allows entropy to increase on ever larger scales, sustaining the arrow of time far into the future. Another important part of the story involves gravity. Gravity pulls matter together, creating stars, galaxies, clusters, and filament-like structures that span millions of light years. At first, you might think gravity's tendency to compress matter contradicts the direction of entropy. But when gravitational systems collapse, they ultimately increase entropy in profound ways. When a cloud of gas collapses to form a star, the gravitational potential energy transforms into heat. That heat radiates outward, raising entropy in surrounding space. Stars burn fuel, releasing energy that spreads across vast distances. The same star may eventually explode, distributing heavy elements into space. Each of these irreversible processes contributes to the forward drift of time. Expansion interacts with gravity in a subtle way. Gravity tries to pull matter together. Expansion stretches the distances between large structures. The balance between these influences has shaped the history of the universe. In the early cosmos, gravity had more influence because matter was closer together. As the universe expanded, matter spread thinner, reducing gravity's large-scale effect. This shift allowed expansion to dominate, accelerating the separation of galaxies. This ongoing interplay creates a directional evolution that extends the arrow of time across cosmic scales. If you examine the universe today, you'll notice that galaxies are not evenly spread. They form clusters held together by gravity, with wide gaps between them. These gaps grow over time as expansion continues. Light emitted by distant galaxies becomes increasingly stretched, losing energy as its wavelength increases. This stretching does not violate energy conservation in the familiar sense, but instead reflects the cosmological structure of space-time. The loss of energy from light contributes to the larger story of entropy rising. Once light is stretched, it cannot spontaneously unstretch. The process is irreversible, reinforcing the forward direction of time. Considering these ideas raises an interesting question. What if the universe were contracting instead of expanding? Would time reverse? The laws of physics allow contraction mathematically, but contraction would not necessarily reverse the arrow of time. For time to reverse in a meaningful sense, entropy would need to decrease. A contracting universe could still have entropy rise, depending on how matter and energy behave during the contraction. The contraction itself would not guarantee a reversal of direction. This reinforces the idea that expansion does not cause the arrow of time. It supports the conditions under which entropy increases but does not enforce the arrow directly. You can think of it like a cooling room. A cooling room doesn't force objects to behave in certain ways, but it creates conditions where specific outcomes become more likely. Expansion does something similar. It creates new regions of low density where irreversible processes can occur. Those processes feed the arrow of time. At the same time, expansion influences the horizon of what you can observe. As galaxies move farther away, some eventually cross what's known as the cosmic horizon, the distance beyond which light can no longer reach you, because the space in between expands too quickly. As galaxies cross this boundary, they become permanently inaccessible. This introduces another kind of irreversibility. Information about distant regions becomes lost to you, not because it's destroyed, but because expansion prevents it from ever arriving. That loss of access reinforces direction. You gain new information from your past, but you lose access to information in your cosmic future. You never recover what expansion carries beyond your reach. The cosmic microwave background, the soft glow filling the universe, also plays a role in understanding the arrow of time. This radiation is the remnant of the early universe's hot phase. As the cosmos expanded, the radiation cooled and stretched. You observe it today as a nearly uniform signal. Its temperature variation is tiny, but that tiny variation seeded the formation of galaxies. Expansion allowed those variations to grow into the structures you see. Without expansion, the early uniformity would have remained, and entropy would not have had such a wide landscape to increase into. Expansion also shapes how long stars can shine. As the universe grows, the density of hydrogen decreases. Stars form more slowly. The universe ages. Over immense timescales, expansion will lead to a future where new stars become rare. Existing stars will burn out. Galaxies will dim. Energy sources will fade. That distant future will not reverse the arrow. It will extend it. Entropy will rise as stars exhaust their fuel and black holes release radiation. Time's direction remains consistent because irreversible processes continue. If you imagine tracing the arrow of time backward, expansion offers clues about what lies at the beginning. As you move back in time, the universe becomes hotter and denser. Entropy decreases. Structures dissolve. Differences flatten. Eventually you reach a point where the universe was so uniform that the arrow of time had not yet emerged. Only as expansion allowed entropy to grow did direction appear. Going backward removes the arrow. Going forward strengthens it. This provides a way of understanding why time feels so steady. The arrow is not tied to local events alone. It is anchored in the entire history of the cosmos. Every irreversible event you observe today is part of a chain that extends back to early conditions shaped by expansion. You're experiencing not just the consequences of entropy increasing here on Earth, but the consequences of how the universe evolved on the largest scales. The tea cooling on a table, the candle burning, the footsteps in snow. All these small arrows are connected to the cosmic one. It's interesting to note that expansion introduces possibilities that would not exist otherwise. If the universe were static, matter would eventually collapse under gravity, forming a dense state where change becomes limited. Expansion prevents that outcome. It allows complex systems to form and evolve. As those systems evolve, they create irreversible traces. These traces anchor your memories, shape your experiences, and define your understanding of time. Expansion supports the growth of complexity, and complexity relies on entropy's increase. Without expansion, both complexity and direction would be much harder to explain. This doesn't mean expansion is the sole cause of time's arrow, but it is an essential part of the foundation. It gives entropy room to grow. It gives systems room to explore new configurations. It gives irreversible processes room to unfold. That unfolding creates the world you navigate each day. You might notice that the direction of time feels a little less mysterious. The arrow isn't imposed on the universe like a rule. It arises from the way the universe began, the way it continues to expand, and the way entropy evolves. The stars drifting apart above you are part of the same story as the cooling drink in front of you, or the fading memory of something that happened yesterday. Expansion ties the smallest events to the larger structures. If you pause for a moment and think about everything your body does without you noticing, it becomes clear that life depends on an intricate sequence of events. Cells divide, energy flows, molecules interact, signals travel. These processes happen in a particular order, and each one relies on the step that came before it. None of them would work if time flowed backward or stopped having direction. Even the simplest biological functions require a world where processes unfold in one orientation. Life is a pattern built on change, and change only makes sense when there's a before and an after. The first place to look is inside a single cell. Though much smaller than anything you can see without a microscope, a cell is full of constant motion. Molecules bump into each other, form bonds, break apart, and drift through the cell's interior. Enzymes fold into shapes that allow them to trigger reactions. Nutrients enter, waste leaves, and signals spread. All these steps must happen in a sequence. If the sequence were to reverse, the reactions would not produce meaningful outcomes. They would break down into states with no biological purpose. The one-way direction of these reactions is what makes metabolism possible. This reliance on direction becomes even clearer when you consider how cells use energy. Every living organism depends on capturing energy from its environment and converting that energy into useful work. Plants take in sunlight and use it to build sugars. Animals consume food and break it down to release stored energy. Bacteria absorb nutrients directly from their surroundings. In all cases, the process requires energy to move from a high-quality, concentrated form into a lower-quality, dispersed one. That downward shift is only possible because entropy rises. If energy could spontaneously flow from low concentration to high concentration, the entire logic of metabolism would collapse. The stability of life comes from the fact that energy always moves from usable to less usable forms. Another important aspect of life's reliance on time's direction is replication. DNA encodes instructions for building and maintaining an organism. When a cell divides, these instructions must be copied accurately. The copying process is made possible by a series of irreversible steps. Enzymes unwind the DNA strand. Other enzymes read the sequence and build a complementary strand. At each step, chemical bonds form in a direction that is not reversible under normal conditions. If the process were to run backward, the DNA would unravel into disordered components. Without a forward direction, copying DNA becomes impossible, and without copying DNA, life cannot grow or reproduce. You can appreciate this even more when you look at how proteins fold. Proteins are long chains of amino acids that must fold into precise three-dimensional shapes to do their work. The folding process follows pathways guided by energy gradients. The chain moves through a landscape of possible shapes, gradually settling into one that is stable and functional. This settling process is not reversible. Once a protein finds its shape, it stays that way unless conditions disrupt it. If time moved backward, the protein would not remain stable. It would unravel, losing its function. Life depends on proteins staying folded, which depends on the one-way nature of energy dispersal. The direction of time also plays a role in how organisms respond to their environment. When something happens around you, a sound, a scent, a flash of light, your sensory systems convert that event into signals. These signals travel through your nervous system, following pathways created by past experience and shaped by responses that unfolded earlier in life. Each signal triggers another. Each reaction builds on a previous one. If time didn't move forward, these sequences would not make sense. Signals would not travel correctly. Reactions would not align with events. Coordination would fall apart. The ability to sense and respond depends entirely on a stable ordering of moments. Memory offers another window into why life needs time to move forward. Earlier, you explored how memories form through irreversible changes in the brain. These changes make learning possible, but learning itself depends on the build-up of experiences. You go through the world, observe patterns, form associations, understand consequences, and adjust your behavior. Each of these steps requires that the past be fixed and the future be open. If time ran in reverse, the meaning of memory would dissolve. You would not learn. You would not grow. The continuity of your identity relies on a directional arrow. Even simple organisms have forms of memory. Bacteria can respond more effectively to nutrients if they've encountered them before. Plants adjust their growth based on previous light exposure. These responses do not require conscious awareness, but they do require irreversible physical changes. Without these changes, organisms cannot adapt. Adaptation itself is a forward-moving process shaped by the arrow of time. Evolution, the long-term story of life on Earth, provides another powerful example. Over billions of years, organisms have adapted to their environments through gradual changes in DNA. Random mutations introduce variations. Environmental pressures select which variations survive. The survivors pass their genes to offspring. This process cannot run backward. If it did, organisms would gradually lose their adaptations, returning to earlier forms that no longer fit their environments. Evolution only makes sense when time has direction. Its entire framework relies on accumulation of changes, of adaptations, of genetic variations. Without the forward movement of time, the tree of life would never have grown its branches. The arrow of time also shapes ecological systems. Predators hunt prey, plants grow toward light, nutrients cycle through soil, water, and living organisms. These cycles depend on a predictable order of events. If time's direction shifted or reversed, the flow of energy through ecosystems would break down. Plants would release energy instead of storing it. Animals would ungrow instead of grow. The interactions that maintain balance would dissolve. Even something as simple as a seed sprouting depends on irreversible steps. Water entering the seed, enzymes activating, tissues forming, energy shifting toward growth. Each stage builds on the previous one. Without direction, the sequence would not happen. Life on Earth also depends on external processes that rely on time's arrow. The sun converts hydrogen into helium through nuclear fusion, releasing energy that drives the climate, fuels photosynthesis, and supports ecosystems. This process is irreversible. The sun cannot convert helium back into hydrogen in the same sequence. The energy it emits travels outward, eventually dispersing through space. If time did not move forward, the sun's energy production would not work. The entire web of life that depends on sunlight would collapse before it began. Even weather systems have built-in direction. Heat moves from warm regions to cooler ones, driving winds, currents, storms, and seasons. Plants time their growth to these patterns. Animals migrate or hibernate in response. You schedule your life around them. Without the forward movement of energy, these patterns would not exist. Weather would become static. The Earth's surface would no longer redistribute heat. Life thrives on these shifts because they create cycles of opportunity. Those opportunities only appear because irreversible processes push the environment forward. As individuals, humans make decisions based on predictions about the future. You plan meals, schedule appointments, prepare for events, and think about long-term goals. These predictions rely on the assumption that the future will follow from the past. If time were reversible, those assumptions would no longer hold. Planning would be incoherent. You couldn't learn from mistakes because mistakes might not remain mistakes. You couldn't anticipate outcomes because causes might not lead to effects. The simple act of making a choice requires believing that your action will influence what comes next. That belief depends on the arrow of time. Communication also depends on time's direction. When you speak, your words travel through the air, creating sound waves that reach another person's ears. The listener hears the sound, interprets it, and responds. This sequence happens in a specific order. If time moved backward, communication would unravel. Words would return to your mouth. Sentences would unform. No exchange of meaning could occur. Language relies on irreversible physical processes. The movement of air, the firing of neurons, the interpretation of signals. These processes require a consistent orientation in time. Societies themselves rely on the arrow of time. Traditions form because events accumulate. Knowledge grows because discoveries build on earlier discoveries. Cultures change because people respond to previous generations. History unfolds because each moment becomes part of a larger story. None of this could happen if time were reversible. Societies would not progress, innovate, remember, or adapt. They would stagnate in a timeless state where no direction exists. The growth of knowledge also depends on irreversibility. Science advances through experiments that leave measurable outcomes. These outcomes only make sense when past events are fixed and can be referenced. If an experiment could reverse itself, the knowledge gained from it would vanish. Every step in understanding the world requires the stability of past outcomes. Without that stability, you would live in a world where no conclusion could be trusted because the evidence might unhappen. Even the simple experience of aging reveals how deeply life depends on time moving forward. Cells accumulate changes. Tissues develop and then wear down. The body adapts, repairs, and eventually reaches limits. These changes are irreversible because they depend on chemical and physical processes that do not run backward. Aging isn't caused directly by entropy, but entropy shapes the conditions under which biological systems degrade. Without the arrow of time guiding these processes, aging would not occur, but neither would growth. Life would not begin, mature, adapt, or end. It would simply fail to exist. Death itself reflects the forward movement of time, but rather than viewing this as a limitation, it helps to see that without irreversible processes, there could be no birth. The existence of life requires the possibility of both beginnings and endings. The arrow of time allows organisms to emerge from simpler components, develop complexity, create meaning, and leave behind traces that shape the future. Every living system is part of this ongoing sequence. You can also see how the arrow of time creates opportunities for life to flourish. Natural selection depends on variation. Variation depends on mutation. Mutation depends on irreversible changes in DNA. These changes, though sometimes harmful, also provide a path for new traits to evolve. Without this path, life would remain static and fragile. The arrow of time creates the space for diversity to grow. It provides the conditions for complexity to emerge from simplicity. If you imagine a world where time has no direction, it becomes clear why life cannot arise. In such a world, no sequence of events would accumulate. Conditions would not evolve. Chemical reactions would flicker without pattern. Structures would not persist long enough to build on themselves. Life depends on stability and change occurring together in a specific balance. Stability holds structures in place long enough for patterns to form. Change pushes those patterns forward. Both of these depend on irreversible processes. Even the very notion of meaning rests on the arrow of time. You find meaning in moments because they happen once and leave traces. If time could reverse, nothing would carry significance. Events would not build on one another. A joyful moment would be undone. A sorrowful moment would lose context. Meaning arises because experiences accumulate and shape your understanding. Without direction, nothing would settle into place long enough to shape anything. As you let these ideas settle, it becomes clearer that life doesn't merely adapt to the arrow of time. Life requires it. The one-way drift of processes makes metabolism possible, supports learning and memory, enables evolution, allows communication, sustains ecosystems, and shapes societies. The arrow is not a constraint holding life in place. It is the framework that makes life possible at all. When you think about time moving forward, it's natural to wonder whether that forward line stretches on forever, or whether it eventually reaches some kind of boundary. You move through your days feeling the constant nudge of moments passing, one after the other, always in the same direction. Nothing ever loops back. Nothing ever resets to an earlier state. That feeling is so steady and familiar that imagining an end to it can feel almost impossible. Yet the question sits quietly in the background of many thoughts. If time has a direction, does it also have a stopping point? Or does it continue as long as there is something in the universe capable of changing, reacting, or unfolding? To start exploring this, it helps to remember that the arrow of time is not a separate substance moving through the world. It's a pattern that emerges from how systems evolve. Time moves forward because entropy increases. As long as there are processes capable of changing states irreversibly, time has direction. But if there were ever a moment when entropy could no longer increase, when the universe reached a kind of equilibrium, then the arrow might lose its anchor. Not because time itself would stop, but because nothing would remain to mark its passage. No new gradients, no new reactions, no new transformations. Just a vast, unchanging state. Thinking about this gently helps avoid the sense of finality the question might bring. It's not about time suddenly halting in the middle of an event. It's about whether the conditions that give time its shape can last forever. The universe gradually evolves as stars burn fuel, galaxies drift apart, and energy spreads across expanding space. These irreversible processes sustain the arrow, but they also raise the possibility that the universe might eventually run out of ways to support change. To understand whether the arrow of time could end, you must look at how the universe behaves over very long stretches of cosmic time. One of the most significant processes shaping the far future is the burning of stars. Stars shine because they convert hydrogen to helium, releasing energy. This process drives weather patterns, provides warmth to planets, and supports life where conditions allow. It also releases heat into the surrounding environment. Over time, stars exhaust their fuel. Smaller stars take trillions of years to die, while larger stars burn out more quickly. But regardless of size, each star eventually reaches a point where fusion can no longer continue. Once that happens, the star cools, collapses, or expands depending on its mass, but the outcome is always irreversible. The energy it once produced becomes dispersed. This gradual depletion of stellar fuel means the universe will eventually enter an era where new stars no longer form. Galaxies will dim. Regions that once held sources of heat and light will cool. Entropy will continue to rise as energy spreads out. Nothing about this trend suggests the arrow of time will reverse. Instead, it suggests the arrow persists into these distant eras as long as processes remain possible. Even as stars fade, there remains white dwarfs, neutron stars, black holes continue evolving. White dwarfs cool. Neutron stars release energy. Black holes interact with their surroundings. Each of these steps pushes entropy higher. Black holes add something especially interesting to this conversation. They gather matter and energy, concentrating them in extremely dense regions. At first glance, this might seem like a reversal of the trend toward disorder, but black holes increase entropy in a dramatic way. The surface area of a black hole, known as its event horizon, is directly related to its entropy. When matter falls into a black hole, the entropy of the universe increases. Later, as black holes evaporate slowly through Hawking radiation, they release energy into the universe in an irreversible process. This evaporation takes an unimaginably long time, but it contributes to the arrow of time in a way that extends far beyond the life of stars. Eventually, After immense stretches of cosmic time, black holes themselves will disappear. Their evaporation creates a universe filled with low-energy radiation spread thinly across space. At this stage, matter as you know it will hardly exist. Most of the energy will be uniformly distributed. Few, if any, processes will remain that can create significant change. This future does not represent an abrupt halt to time. Instead, it reflects a gentle fading of the arrow. Once entropy reaches a maximum, if it ever does, the universe no longer has a pathway to create meaningful differences between one moment and the next. Without differences, there is nothing to mark the passage of time. This scenario is often called heat death, not because it is violent or fiery, but because everything becomes uniform. Every region reaches the same temperature, no gradients remain, no structure persists. Without gradients, processes cannot occur. Time still exists as a coordinate, but the arrow disappears because nothing meaningful changes from one moment to the next. In such a universe, asking whether time continues becomes difficult because time is defined by change. If nothing changes, time cannot be experienced. This does not mean time ends in a dramatic sense. It means the universe becomes so still that the distinction between earlier and later loses meaning. The arrow dissolves quietly because the conditions that created it no longer exist. Entropy has reached its limit. All the irreversible processes have already played out. The universe has settled into a state where no new change can arise on its own. But this is not the only possibility. The future of time depends heavily on the long-term behavior of the universe's expansion. If expansion continues accelerating, as observations currently suggest, the universe will spread out more and more quickly. Over time, regions will become isolated. Galaxies will drift beyond each other's reach. Stars within a galaxy will remain gravitationally bound, but the space between galaxies will expand so rapidly that even light cannot bridge the gap. This accelerated expansion would create a universe where different regions slowly lose contact with one another. The isolation increases entropy in its own way because it removes potential interactions. The arrow of time would continue as long as processes exist within galaxies, but the universe would feel increasingly empty. Eventually, even within galaxies, stars would burn out, leaving behind remnants that cool and fade. The universe becomes quieter, but the arrow persists as long as cooling, decay, and evaporation continue. In another speculative scenario, if the acceleration of expansion changes over time, the universe might reach a point where expansion slows and reverses. In this case, the universe would contract. The contraction would bring matter and energy closer together. At first glance, this might seem to suggest the arrow of time could reverse as well, but contraction itself does not cause entropy to decrease. Collapsing structures generate heat and increase disorder. Dense regions become hotter. Reactions become more chaotic. Entropy rises faster. In a contracting universe, the arrow of time continues pointing in the same direction because irreversible processes continue to occur. As the universe contracts further, the density and temperature would increase dramatically. The arrow would not reverse. It would intensify. Eventually, if contraction continued all the way to a single point, it might resemble the earlier state of the universe. But the conditions would be extremely different. The early universe had low gravitational entropy. A contracting universe approaching collapse would have extremely high entropy. This difference prevents the arrow from reversing. There is also the possibility that new regions of space-time might form through quantum fluctuations. In some models, expansion does not end uniformly. Instead, it produces pockets where conditions allow new universes to form. These scenarios are speculative, but they raise interesting questions about whether new arrows of time could emerge in new regions. If a fluctuation creates a low entropy bubble, that bubble could develop its own arrow. Entropy would rise within it, and observers inside it would experience time moving forward, just as you do now. From your perspective, this does not reverse your arrow. It simply creates more arrows. These possibilities illustrate that the arrow of time is tied to physical processes, not to some external timekeeper. Time continues as long as processes can occur. When processes cease, the arrow quiets. That does not make time vanish. It makes time lose meaning because meaning relies on difference. Without difference, there is no before or after in any functional sense. You can think of it like a book with no printed words. The pages still exist. They still have order. But there is nothing on them to communicate meaning. A universe in heat death has pages with no writing. Time exists as a dimension, but has nothing to carry along it. The arrow requires content. It's also helpful to remember that the end of the arrow of time, if it ever arrives, lies in a future so distant that it surpasses ordinary imagination. The process is happening now: stars burning, planets orbiting, organisms evolving, memories forming, are part of a universe still rich with gradients and complexity. The arrow is strong because the universe is full of differences waiting to resolve. Billions of years from now, those differences will look different, but the arrow will persist as long as change continues, even in subtle forms. If you bring this idea back to a more personal level, you can see how the arrow shapes not only the universe, but your experience of it. Your life moves through cycles of growth, learning, and interaction. Each moment creates traces that shape the next. As long as you live, time's arrow is deeply meaningful. It structures your memories, your intentions, your identity. The distant cosmic future, where the arrow might fade, has no bearing on the direction you experience now. For you, the arrow remains steady. Letting this thought settle, you can see that asking whether time has an end is really asking whether change has an end. If the universe eventually becomes too uniform for change to occur, the arrow fades. If new processes continue, the arrow endures. The other way, the direction you experience today arises from a universe still full of possibility.